Hello and welcome to this new course of multivariable calculus or CALCULUSIII. The subjects that we are going to address within this presentation are briefly, at first, vectors and geometry in space, which is more of a prerequisite about things that you should already know, but that are fundamental. Then vector valued functions, including parametric curves, arc lengths, limits, curvature, calculation of torsion and motion in space, even more than that. Partial derivatives, including multivariable functions, limits, continuity, tangent planes, directional derivatives, max and min values. Then the third part, multiple integrals, like double, triple integrals, area, mass, and center of gravity calculation. And finally, vector calculus, like vector fields, line integrals, fundamental theorem of integration, Green's theorem, parametric surfaces, and surface integral, including Stokes Theorem and Divergence Theorem. Let's start with a review and building the foundation for vectors and geometry in space. At first, what is a vector? A vector is a mathematical object that has magnitude, or length and size, and direction. It points somewhere. A vector is not a simple point, it's an arrow linking two points in space. An example for that, velocity and force vectors. A 2D vector representation is given by v equal vx and vy, where vx and vy are the coordinates of that vector, which are the coordinates of that point that is away from the origin of the axis, okay? And this vector links these 2 points, the origin and the vx, vy here, the point having these coordinates. This is by definition a vector. Or another representation, another way to write it is v equal vxy, or v equal vxi plus vyj, okay? That's x of v and that's y of v. Vx is the x-axis component and vy is the y-axis component. I and j are unitary vectors that refer to pointing to x along x and along y respectively. Again, the vector is represented by v equal vx vy, where vx and vy are the coordinates of the vector in the xy system, or another form for that is v equal vxi plus vyj. I and j are respectively the unitary vectors for the x and y axis. This is geometrically an arrow, which is the vector here, an arrow from 0, 0, which is the origin of the axis, to vx, vy. As for the vector magnitude or length of the vector, if you imagine the vector, it has a vy component, which is the height of the vector, and vx, which is the tread. So applying the law of Pythagoras, because we have a rectangular triangle, v square is equal to vx square plus vy square. So v, which is the length of the vector, is equal to square root vx square plus vy square. The direction of the vector is given by the angle theta it makes with the positive x-axis. So tan theta in trigonometry is equal to the opposite side divided by the adjacent side, or vy divided by vx. So theta is equal to tan to the power of -1, or arctan, the inverse of the tangent of vy divided by vx. Of course, the angle would be given in radians. Consider two vectors u having the coordinates ux, uy, and v, vx, vy. What are the different operations that apply to these vectors? At first, addition, u plus v. The addition and subtraction, both of them give you a new vector. So u plus v is equal to a new vector having the coordinates ux plus vx as x-axis coordinate, and uy plus vy for the y-axis. Subtraction, the same thing. U minus v equal a new vector having ux minus vx and uy minus vy. Another operation is the scalar multiplication. So what does a scalar multiplication do? Scaling means that you are increasing the length or decreasing the length of the vector, or you are changing sense, the direction from positive to negative. This is what the scalar does. It is a real number multiplied by both of the coordinates to increase its length or decrease it if k is less than 1. Another operation is the dot product. U dot v is equal to ux vx plus uy vy. It is a scalar operation, meaning that it gives you a resultant of the two vectors, which is equal to the magnitude of u multiplied by that of v multiplied by cosine theta. Visually, you have the vector u dot v, and the resulting vector is the diagonal crossing the parallelogram formed by the two being the two sides of this parallelogram. So this is u dot v, or vector w. Determinant or 2D cross product equivalent. U cross v is equal to ux vy minus uy vx. This is how you solve it. So determinant of ux, uy, you place them vertically, and vx, vy. You multiply ux by vy like this, and then you multiply by minus uy times vx. So it is equal to ux vy minus uy vx, just like you solve the determinant of a matrix. 3D space vectors, you have u equal ux uy uz. In this case, we have 3 components instead of 2. Another representation is equal to uxi plus uyj plus uzk, where I, j, k are the 3 unitary vectors for xyz axes respectively. V equal vx vy vz. Also another form is v equal vx vy vz within parentheses. Geometrically, it is an arrow starting from 0, 0, 0, the origin of the 3D axis, to ux, uy, and uz, just like the illustration to the right, to the bottom right in this picture. Magnitude. Just like in 2D space, the same concept applies here. The magnitude of a vector u is equal to the square root of ux squared plus uy squared plus uz squared. For the operations, the same thing. So u plus v gives you another 3D vector, which is equal to ux plus vx, uy plus vy, and uz plus vz. U minus v is equal to ux minus vx, uy minus vy, and uz minus vz. Scalar multiplication, the same concept as in 2D. You are scaling the vector either by increasing the length or decreasing it. If k is greater than or equal to 1, you are increasing. Otherwise, if it is less than 1, then you are decreasing. If it's negative, then you are inverting the direction, the heading of this vector. So ku is equal to k multiplied by ux, uy, and uz. Dot product, u dot v is equal to ux vx plus uy vy plus uz vz is equal to the size of u times the size of v times cosine theta. So cosine theta is equal to u dot v divided by the size of u times the size of v. We can get the angle of this vector. The cross product in 3D uses the same concept as that in 2D. But the calculation is a little bit different. So let's say you have two vectors, u, ux, uy, uz, v, vx, vy, vz. U cross v is equal, on top you place the unitary vectors respectively I, j, k. Then after that, the coordinates of the first vector u, which are ux, uy, uz respectively. Then the ones of v, vx, vy, vz. Okay, for I, so you cross or you bar the line and the columns where they intersect at I, and then you multiply what's underneath them in the method of determinants. So I times ux vz minus vy uz minus, here another thing to pay attention to, you have plus minus plus. So minus j, and j is where a line and a column intersect. So you leave them out, then you multiply ux vz minus vx uz, then plus k times ux vy minus vx uy. So u cross v is equal to uy vz minus vy uz, then minus ux vz plus vx uz, or uz vx, plus k, or plus ux vy minus vx uy. Another thing to note is that when the dot product between two vectors is 0, it means that they are perpendicular or right angled to each other. In other words, the length of the projection of the one over the other is 0. There's no projection. So whenever you get a dot product that is 0, it means that the two vectors are normal to each other. They are perpendicular to each other. Why? Because the projection of the first, just like if you look at z and x, if you regard them or imagine them as two vectors, the projection of z over x is 0. It has no projection. Okay, it falls, its shadow is right underneath it, so to speak. Any vector, now, another thing, any vector can be converted to a unitary vector through dividing it by its magnitude. So v is equal to the normal or the ordinary vector v. Okay, v is the unitary vector. V equal v as a vector divided by the size or length of v. This is how you get the unitary vector of v. Line and plane equations in space. Consider a line in space passing by a point P0 having the coordinates x0, y0, z0, and having a directional vector, which is of course parallel to it, u equal ABC. These are the coordinates for the vector. The parametric equations or equation of this line is given by P0, again, is a point, and u is the directional vector. R equal R0 plus TU. R is a random point on the line with R having the coordinates x, y, z. R0 is the vector for a well-defined point, and T is a real parameter. Then the parametric equation of that line is given by the following. X equal x0 plus at. Again, x0 belongs to the point, that's the first coordinate of the point, and a belongs to the vector. Y equal y0 plus bt, and z equal z0 plus ct. x0, y0, z0 are the coordinates for the point p0, and abc are those of the directional vector. T is the parameter that moves along the line. Exercise. Find the equation of the line having a defined point P0, 1 minus 2, 3, and a director vector V, 4, 0, minus 1. Of course, these are the coordinates of the vector, just like 1 minus 2, 3 are those of the point P0. The parametric equation is given by x equal x0 plus at, y equal y0 plus bt, z equal z0 plus ct. Of course, you can try at it yourself before seeing the solution. x0, y0, z0 are coordinates of p0, abc are those of the vector. Then x is equal to 1 plus 4t, that's 1, plus 4t, y equal 0t minus 2, which is minus 2, z equal 3 minus t. Let's get rid of t and see what happens. So z equals 3 minus t, then t equals 3 minus z. We will replace the value of t in the first equation. So you get x is equal to 1 plus 4 times 3 minus z. So x is equal to 1 plus 12 minus 4z. And you place underneath it y equal minus 2, and you add up left and right, both of the sides of the equations. So x plus y is equal to minus 2 plus 1 plus 12 minus 4z. Then you get the equation of a plane containing that line. If neither of a, b, and c is 0, we can remove t and write the equation using this form. X minus x0 divided by a is equal to y minus y0 divided by b equal z minus z0 divided by c. This shows how each coordinate changes proportionally along the directional vector. Going back to planes. What is a plane? A plane is a flat surface defined by a point P0, x0, y0, z0, and a normal vector n forming a right angle 90 degrees with that plane. Equation of the plane. Let's consider a random point mxyz located on the surface of the plane. The dot product between the vector formed by m and p0, which is a very defined point over the plane, and the normal vector n, which is normal to the plane itself, is 0. Hence, vector p, which is p0m, by the way, this is how we get this vector. The vector between 2 points is given by the coordinate of the first minus the coordinate of the second on the 3-axis. So x minus x0, y minus y0, and z minus z0. Dot the vector n, which is normal to the plane, is equal to 0. So x minus x0 times a plus y minus y0 times b plus z minus z0 times c is equal to 0. This is the equation of the plane. Now, if p0 was the origin of the axis, meaning that x0, y0, z0 is equal to 0, then the equation of the plane becomes ax plus by plus cz equal 0. Consider a line L with a directional vector d and the plane P with a normal vector n. So how do we get the angle between the line and the plane? This angle between the line L and the plane P is given by a relationship that we're going to deduce from this illustration here. So you have the director of the line, this is the line L, and this is the normal vector. At first, cosine alpha, which is not the angle between the line and the plane, but rather the one between the line and the normal vector, is equal to n dot d divided by the modulo of n times the modulo of d. Modulo means the size of n multiplied by the size of d. What is the relationship, however, between alpha and theta, which is actually the angle between the line and the plane? Cosine alpha is equal to cosine 90 degrees minus theta, because alpha is 90 degrees minus theta, which is equal to sine theta is equal then to d dot n divided by the length of d times the length of n, or the size or magnitude of d times the magnitude of n. This is how we get theta. From sinus theta, you can get theta easily by inverting the sinus. The angle between the line L and the plane P again is given by sine theta equal d dot n, dot product between the two vectors, the director and the normal vector to the plane, divided by magnitude of d times magnitude of n. If the line and the plane are parallel, then d dot n is equal to 0. Why? Because the directional vector in such case would be perpendicular or normal to the n vector of the plane, just like you see in this picture here. The red line, which you can consider as a line on top of the plane, is parallel to the plane, of course, then it is perpendicular or normal to the n vector. If two planes are parallel, then their normal vectors are parallel as well. So n1 would be equal to k times n2. In other words, what differentiates between both normal vectors is the scale. Why? Because they are going in the same direction. So they are almost the same. What's different is the scale. So one is more lengthy than the other, or vice versa. K, of course, is a real number. The angle, however, the formula of the angle between the two planes is given by cosine theta is equal to n1 dot n2 divided by size of n1 or magnitude of n1 times magnitude of n2. As we note that n1 dot n2 is equal to size of n1 times size of n2 times cosine theta. So these cancel out in the numerator, you are left with cosine theta. This is how we got this equation. Also, another thing, the intersection between two planes is a line that we can find by solving the system of equations of both intersecting planes. Exercise. Find the angle between the two planes, P1 and P2. P1 given by 2x minus y plus 2z equal 5, P2 given by x plus 2y minus 2z equal 3. At first, as a reminder, what is the equation of a plane? It is given by x minus x0 times a plus y minus y0 times b plus z minus z0 times c is equal to 0. As you notice, a, b, and c are the coordinates of the vector, of the normal vector of the plane. And these are the same arguments multiplied by x, y, and z respectively. So in other words, for P1, for instance, the normal vector is given by 2, minus 1, and 2. These are a, b, and c respectively. The same thing for P2. So n is the normal vector which is perpendicular to the plane, which has the coordinates ab, or the arguments a, b, c, the same arguments that we see in the equation for the plane, which are the same arguments multiplied by x, y, z respectively. So for P1, n1 is equal to 2 minus 1, 2 for the second plane, and 2 equal 1, 2 minus 2. Then, also another way of looking at it, the normal vector is equal to the derivative of the equation of the plane in respect of x, y, and z. Okay, it gives you the three arguments for the n vector, or ABC respectively. Okay, so the angle between these two planes is given by cosine theta equal n1 dot n2 divided by length of n1 times length of n2. As a reference, I'm gonna place n1 and n2 to the top right, as you see, to use them within the equation of the cosine. So cosine theta is equal to the absolute value of the dot product between n1 and n2, which is 2 times 1 plus minus 1 times 2 plus 2 times minus 2, divided by the scale, or the size of n1 times the size of n2, which is square root of 2 square plus minus 1 square plus 2 square, which is square root of 9 times square root of 9, because the norm or size of the second vector is the same. It is square root of 1 square plus 2 square plus minus 2 square. It gives us 4 over 9. So theta is the arc cosine, or cosine to the power of minus 1 of plus 4 divided by 9, approximately 1.11 radians. Now we can get this value in degrees. So pi radian is equal to 3.14159. Then theta in degrees is equal to the radian value, which is 1.11 times 180 divided by pi, approximately 63.6 degrees. Exercise. Find the equation of the plane given that we have P1 to 3 is a point lying on the plane, n 2 minus 1, 1 is a normal vector to the plane passing by point P. So, if you want to solve it, to try add it, you can do that. Otherwise, let's continue. V, or the director vector that is between the point P that is well defined and a random point that we choose on the plane, is given by x minus 1, y minus 2, and z minus 3. Or in other words, x minus x0, y minus y0, and z minus z0. As for the normal vector, we already have it. It is 2 minus 1, 1. As a reminder of the plane equation, it is given by a times x minus x0 plus b times y minus y0 plus c times z minus z0 equals 0, which is the dot product between these two vectors, basically. Alright, so again we assume m as a random point on the plane. The vector linking m with p0 is v, so n dot v is equal to 0. So n dot v is equal to nx vx plus ny vy plus nz vz is equal to 0. Then x minus 1 times 2 plus y minus 2 times minus 1 plus z minus 3 times 1, of course, is equal to 0. Hence, 2x minus y plus z minus 3 is equal to 0. And the equation of the plane is 2x minus y plus z is equal to 3. checking if point Q312 resides on the plane. Of course, you can try to solve it yourself, but for now, let's move on. We simply plug in xyz of the point within the equation of the plane. The outcome should be 0. So the equation of the plane is 2x minus y plus z minus 3 is equal to 0. This should be 0. So 2x is 2 times the x of q, which is 3, minus y, or minus 1, plus z, which is plus 2, and finally minus 3. It is equal to 6 minus 1 plus 2 minus 3 equal to 4. 4 is different than 0, then q does not belong to the plane. Vector valued functions. So we will start with space parametric curves. What is a parametric curve in space? It is a curve defined by expressing x, y, and z or z in respect of a parameter such as t. That can be a time parameter. It is often a time parameter for motion vectors. So you have x equal x of t, y equal y of t, and z equal z of t, where t is within the real numbers domain. As an example, x equal r cosine t, y equal r sine t, and z equals 0, where this is an equation of a circle of radius r existing in a 2D plane. Of course, that's why z is equal to 0. And t, of course, is the angle. Tangent vector at parameter t. What is the tangent vector? It points in which direction the curve is headed, whether it is going up, which means it is positive, or down, which means it is negative. Okay, the tangent vector, just like in Calculus 1, it shows us how the slope is changing of the curve, whether it is positive, so the curve is heading upward, it is an upward curve, or downward when it's negative. It is the derivative of RT in respect of t on the 3 directions, x, y, and z. Exercise: find the tangent vector, the unit tangent vector, and evaluate both at t equal 1 for the following function: rt equal t squared, and t to the power of 3. At first, the tangent vector is given by, of course, you can try at it yourself. You can pause the video and try to do it. So t equal r prime t, which is the derivative of r in respect of t on the 3 axes, on the 3 directions, or in the 3 dimensions rather, is equal to derivative of t 1, then 2t, then 3t squared. That's the tangent. The unit tangent vector is given by t divided by what? So tu is equal to t divided by the modulo, or the size of t. Okay, the size of t is equal to square root 1 squared plus 2t squared plus 3t squared, also squared. Okay, tu then is equal to 1 divided by square root of 1 squared plus 4t squared plus 9t squared, that's the length of the vector, multiplied by the tangent vector, the original tangent vector, which is not unitary, 1, 2t, 3t squared. At t equal 1, what would be the value for both vectors? t1 is equal to 1, 2, 3, that's the original vector, and for the unitary vector, it would become 1, 2, 3 divided by 1 over square root of 14, because if we replace t by 1, you get square root of 1 plus 4 plus 9, which is 14. That's the final answer. Arc length of the curve. The arc length from t equal a to t equal b, which are the bounds of this curve, of where we are measuring the length, is given by L equal integral from a to b, square root of the derivative of x to t squared plus y t squared plus the derivative of z t squared. This is basically the sum of the length of the tangent vectors throughout the curve from point A to point B, which are the 2 boundaries where we are measuring the length of this arc. Exercise: find the arc length of the helix from t is between 0 and 2 pi. Rt is given by cosine t sine t and t. That's the equation of the helix. So L is equal to integral from a to b square root of x prime t squared plus y prime t squared plus z prime t squared dt. These are the respective derivatives for x, y, and z of RT. X prime t is equal minus sine t, y prime t is equal cosine t, and z prime t is equal to 1. So L is equal to integral from 0 to 2 pi square root of minus sine t squared plus cosine t squared plus 1 squared dt equals square root of 2 integral from 0 to 2 pi, which is 2 pi square root of 2. Vector function limits. So let's say we have a vector function given by x equal x of t, y equal y of t, and z equal z of t. Let's consider the parametric equation above. This can be written in two vectorial forms that mean the same thing. Also, you can write it r of t is equal xt I plus yt j plus zt k. I, j, and k are the unitary vectors in the three directions x, y, and z. Another unique form of representation is the following. Rt is equal xt, yt, zt, which is the angular form. The limit exists for r of t when it exists for each and every one of the components of x of t, yt, and z of t, okay, of r of t. Limit r of t when t goes to a is equal to the limit t goes to a for the three components respectively, for x of t, y of t, and z of t, which is equal to limit x of t when t goes to a, limit y of t when t goes to a, and limit z of t when t goes to a. It can also be written using this form, limit x of t, t goes to a, multiplied by I, plus limit y of t, t goes to a for j, and limit z of t when t goes to a for k. Find the limit of the curve when t goes to 0. The following curve is rt equal t squared sine t and e to the power of t. Okay, so limit rt when t goes to 0 is equal to limit t goes to 0 for t squared sine t and e to the power of t, which is equal to 0 squared. Sine 0 is 0 and e0 is 1. So the answer is 0, 0, 1. Now continuity. What is continuity? A vector is continuous at a point A if and only if the limit at that point, limit rt when t goes to a, is equal to ra, to a finite value. So this should apply for the three components x, y, and z as well, for the vector to be continuous at that point. Vector derivative of a curve or over a curve. As a recap, what is a derivative? The derivative of a curve at a specific point is the slope of the curve at that point, which is rise over tread, or in other words, tan alpha. So let's say you have t and t plus h as two boundaries for this curve. The tangent alpha is equal to rt plus h minus rt divided by t plus h minus t, which is h, or rise over tread. In other words, that's tan alpha. That's actually the tangent, which is equal, what we've seen before, for rt, x prime of t I plus y prime of t j plus z prime t k. So it is equal to the derivative of rt on the three components, on the three directions of that curve, on the three axes. Magnitude limit, limit rt when t goes to a, that's the limit for the magnitude of the vector, which is equal to the limit of square root x prime t squared plus y prime t squared plus z prime t squared for t goes to a. So that's the limit of the magnitude, not of the curve itself. Example, rt equal 1 over t squared et. Of course, you can try to solve it yourself. Try to find the limit for rt, then the limit for the magnitude of rt. Okay, now for the limit of rt itself, it is equal to limit when t goes to 0. Okay, this is what we're trying to find, of 1 over t squared and et respectively. It is the limit for the three components. For 1 over t, this is 1 over 0. It goes to infinity. So the limit does not exist, although it exists for y and z, which have the limits respectively of 0 and e to the power of 0 is 1. So we can conclude that this function is not continuous. Now let's find the limit for the magnitude. We need partial derivatives of x prime t, y prime t, and z prime t. X prime t is equal to minus 1 over t squared. Y prime t is equal to 2t, and z prime t is equal to e to the power of t. The limit for the magnitude for t goes to 0 is limit of square root x prime t squared plus y prime t squared plus z prime t squared, which is limit of t goes to 0 of minus 1 over t squared plus 2t squared plus et squared, or 1 over t to the power of 4 plus 4t squared plus e to t. This becomes limit t goes to 0 of 1 divided by 0 plus 0 plus 1. This element here goes to infinity, so the limit does not exist. Therefore, not only the function is not continuous, but also there's no limit for the magnitude, which is as a result for that. We've already referred to vector derivation, but here we will add some rules related to it. du plus v over dt is equal u prime plus v prime. In other words, the derivative of a sum of vectors is the sum of the derivatives of each vector. dfu over dt is equal to f prime u plus fu prime, where f is a function and u is an element, a parameter within the function. So it is equal to the derivative of the function itself multiplied by u plus f times the derivative of the parameter within f. d over dt of u dot v, which is the dot product of the two vectors, is equal to u prime dot v plus u dot v prime. Okay, so it is the derivative of the first vector dot product of the second vector plus u dot the derivative of the vector v. d over dt u cross v also is equal to u prime cross v plus u cross v prime, where u prime and v prime are the derivatives of u and v vectors respectively. Second derivative. So let's say we have a function rt equal xt, yt, zt. The second derivative is, which is also written d squared rt over dt, is equal to the derivative of each of the components respectively, x, y, and z. An application for that, let's say rt is the positive vector in motion physics, r prime t in such case is the velocity vector, and r second t would be the acceleration vector. Vector integral. Let's say we have a function rt equal xt, yt, and zt. So integral of rt dt is equal to integral xt dt I plus integral yt dt j plus integral zt dt plus c, which is a constant vector of integration, or a vector constant of integration rather. So as an example, rt equal 1 to t squared. Let's integrate. I of t is equal to integral 1 dt I plus integral 2t dt j plus integral t squared dt k plus c, which is equal to ti plus t squared j plus t to the power of 3 divided by 3k plus c, or equal t squared t to the power of 3 divided by 3 plus c. Now, where do we use that? As we've learned already, that when we need to get the vector of velocity from the displacement, we derivate. But if we want to go the inverse direction, we integrate. So to get the displacement from the velocity or the velocity from the acceleration, we integrate the function. Curvature and torsion. Curvature measures how fast a tangent direction magnitude changes on a curve. It is given by k equal dt over ds, the change of tangent throughout the curvature, throughout the curve rather, which is these two divided give us the curvature, or k. So t equal r prime t divided by the module or size of r prime t. This is the unit tangent vector. S is the arc length parameter. ds is equal r prime t in length times r prime t, or in other words, like it is an area coefficient, multiplied by r prime t from the unit tangent vector gives us r prime t to the power of 3 in the denominator of the equation. Now r prime t gives us the velocity or tangent vector, or the rate of change of position on rt. R second t gives us the acceleration or the rate of velocity change. So r prime t cross r second t give us how perpendicular the velocity is to the acceleration vector, which is also the bending, okay? Because r prime t cross r second t give us a vector that is perpendicular or normal to both vectors. When these two are parallel, then the cross product would give you 0, okay? So there would be no curvature or no bending at all. Torsion twist. The torsion requires up to the third derivative. It is equal to, it is designated at first by tau, equal r prime t cross product r second t dot r third t divided by the modulo or the size of r prime t cross r second t square. R third t is the change of acceleration. It is, or its dot product with r prime t cross r second t gives the torsion twist. Example, the helix rt equal cosine t, sine t, and t. So let's get the derivatives up to the third degree to evaluate the curvature, then the torsion. R prime t is equal minus sine t, cosine t, 1. R second t is equal to minus cosine t, minus sine t, 0. And finally, r third t is equal to sine t, which is cosine, minus cosine t derivated, then minus cosine t, and 0. So the speed, which is r prime t in length, square root of minus sine t square or x prime t square plus cosine t square plus 1 square equal to square root of 2. Okay, then the curvature is given by, at first let's get r prime t cross r second t, I minus j k, minus sine t, which is for r prime t, cosine t, and 1, r second t, place it at the bottom, minus cosine t, minus sine t, and 0. So this gives us equal 0 plus sine t I minus j, 0 plus cosine t, plus sine square t plus cosine square t k, which is 1. In this picture, we see the function cosine t plus sine t plus t to the left, and to the right, the curvature, which is r prime cross r second t, the first derivative, cross product, the second derivative, divided by r prime t to the power of 3 in length. So the size of r prime t in length to the power of 3, it gives you minus sine t cosine t something plus 1. This is what the curvature looks like. So it is equal to sine t I minus or plus minus cosine t j plus k. After that, so you have curvature is given by r prime t cross r second t equals sine t I minus cosine t j plus k. The magnitude r prime t cross r second t is equal to square root of sine square t plus cosine square t plus 1 equals square root of 2. Then k is equal to r prime t cross r second t divided by r prime t in modulo or in size to the power of 3, or square root of 2 divided by square root of 2 to the power of 3, which is equal to 1/2. Okay, then let's get the torsion. So we've gotten already the curvature. Torsion is equal to r prime t cross r second t dot r to the third derivative t divided by r prime t cross r second t square, the size or the length of this vector square. So r prime t cross r second t dot r to the third t is equal to sine t minus cosine t 1, which is r prime t cross r second t. Here we're not getting the length of this vector. We want this vector as it is in order to multiply it in a dot product with r to the third level of t. So dot sine t minus cosine t 0 equal sine square t plus cosine square t plus 0 equal 1. So r prime t cross r second t square is equal to square root of 2 square, which is 2. Okay, that's, you have in the denominator r prime t cross r second t square give us 2. Hence, tau, the torsion, is equal to this product here, this component which is 1 divided by this component which is 2. So the torsion is equal to 1/2, which is equal to the curvature as well. So this curve has the same curvature, or it bends in the same way it tenses, or it is torsed, it twists, okay, in the same manner or in the same magnitude that it twists, it bends as well. Vectorial motion in space: position, velocity, and acceleration. So let's say we have the following vector function: rt equal xti plus ytj plus ztk. This function describes the position of an object in space in respect of time, or in other words, the movement of this object. To get the velocity or the rate of this displacement, so to speak, we differentiate the vector function to the first degree. So r prime t, which is the velocity vector in this case, is equal to x prime ti plus y prime tj plus z prime tk. Hence, the magnitude of the speed, or the numerical value of that speed, is equal to v equal to r prime t in module, meaning it is the norm or the length of r prime t, equals square root of x prime t square plus y prime t square plus z prime t square. To get the acceleration, we derive the second time in respect of t. So the acceleration of this object in space is equal to r second t equal x second t I plus y second t j plus z second t k. Exercise. A particle is moving in space with a position vector rt equal t square I plus tj plus 2t square minus tk for t greater than or equal to 0, which is normal. For motion and mechanics, t is always greater than or equal to 0, because time moves forward. So find the velocity vector v, acceleration a, and speed at time t equal to. Of course, you can pause the video and try to do it yourself. For now, let's move on. So the velocity v is equal to r prime t, which is the derivative of rt, equal to 2ti plus j plus 4t minus 1k. That's the velocity vector. Then the acceleration is given by a equal r second t, which is the second derivative, is equal to 2i plus 4k. If you get the magnitude, which is square root of 2 square plus 4 square, you can get the real exact value of the acceleration. Now, speed at t equal to is given by v equal, okay, you replace by 2 the velocity vector. So it is 4i plus j plus 7k, which is the value for the vector at 2 here, 4 plus 1 plus 8 minus 1. That's the velocity value at t equal to, which can be 2 seconds, for example. So v equal 4i plus j plus 7k. Of course, you can get the module or the length of this vector. So the exact value for that velocity equal to square root 4 square plus 1 square plus 7 square, or square root of 66. That's the exact answer for the velocity at t equal to. For positional vector describing the motion in space of a particle or an object, given by t square I plus tj plus 2t square minus t, this is the movement, or what the movement looks like, the variation of x, y, z throughout time, throughout the factor of time. Okay, from it, you can get the velocity, which is the derivative of rt given by 2t plus 1 plus 4t minus 1. Okay, this is what the velocity looks like. Partial derivatives. Let's say we have a function of several variables, which is a function that changes in a multidimensional space. So you have in 2D fxy equal x squared plus y squared, which is a disk on a 2D plane where x and y belong, of course, to the real number realm or domain, and x squared plus y squared is a circle on the xy axis. or fxyz is equal to x squared y and z, y times z, which is a function in 3D space. Here you have x, y, and z, 3 dimensions instead of 2. Of course, all of them also belong to the real numbers. So this would be the representation of such function. Let's start at first with limits and continuity. What is the limit of a multivariable function fxy? It is limit fxy when x, y go to a, b simultaneously. So the limit exists for function fxy when the function approaches the same value as x approaches a and y approaches b at the same time, or xy goes to a, b. Continuity, fxy is continuous at a, b when limit fxy, xy go to a, b is equal to fab, which is a very defined point. Partial derivation. A partial derivative measures the rate of change of a function fxy in one direction or in respect of one axis, while of course fixing the other variable, which is considered in this case as constant. So consider a function fxy. In respect of x, f prime x is equal to df over dx. We are deriving in respect of x. X is considered the variable, but y and any other thing within the function are considered as constants. In respect of y, f prime y equal df over dy. Example, fxy equal x squared y plus sine y. We want to derive f in respect of x and y. So at first we treat y as a constant since the variation is xy's. You can try to solve it yourself, of course, and pause the video. F prime xy is equal to partial fxy divided by partial x, which is the derivative of xy, fxy in respect of x, equal to 2xy plus 0, y because y is a constant again, is equal to 2xy. Then we treat x as a constant since the variation is on y-axis. F prime xy is equal partial f xy divided by partial y. So we are deriving in respect of y, which gives us x squared plus cosine y. Another example or exercise, the same thing. fxy is equal to x squared plus y squared divided by xy. At first, there's a fundamental law of derivation for fractions, which is u over v, u being the numerator and v is the denominator. Prime, so the derivation of u divided by v is equal to u prime v minus uv prime divided by v squared. So f prime x y in respect of x is equal to u prime v, which is 2x times the denominator, minus u v prime x2 plus y2 times we are deriving in respect of x, so we are left with y divided by v squared, which is the denominator square, is equal to 2x squared y minus x squared y minus y3 divided by x squared y squared, equal to, if you expand it, x squared minus y squared divided by x squared y. Okay, in respect of y, f prime x y is equal to also u prime v minus u v prime divided by v squared. So u prime v is 2y times xy minus u v prime, or minus x squared plus y squared times x, because we are deriving in respect of y, divided by v squared, or the denominator square, equal to xy squared minus x3 minus xy squared divided by x squared y squared, equal to finally y squared minus x squared divided by xy squared. Hence the partial derivatives for fxy are respectively f prime x xy equal x squared minus y squared divided by x squared y. F prime y xy is equal to y squared minus x squared divided by xy squared. Now let's go to the second order derivative. So f second xy is equal to 2x times x squared y minus x squared minus y squared times 2xy divided by x squared y to the power of 2. We are deriving the derivative. This is how we get the second order, which by the way gives us the concavity, or how the curve is pointing, if it's pointing upward or downward. Equal 2x to the power of 3y minus 2x3y plus 2xy3 divided by x4 y squared, which is equal to finally 2y divided by x to the power of 3. Second derivative in respect of y, and by the way we can do it for both of the functions. Okay, so f second y is equal to u prime v, which is 2y times xy squared minus u v prime minus y squared minus x squared times 2yx divided by the denominator square, which is x squared y to the power of 4. So it is the second derivative in respect of y of f prime y xy, which gives us, if we expand it, 2x divided by y to the power of 3. After that, we want to evaluate the value of these derivatives at point a2, 1. So we simply replace x and y, the coordinates of that point, in f prime x and f prime y. For f prime x, you have 2 squared minus 1 squared divided by 2 squared times 1, or 4 minus 1 divided by 4 equals 3 divided by 4, which is positive. It means that the function is going up in this point. At this point, the slope of the function, the slope of the tangent is positive. As for f prime y, 2, 1 is equal to 1 minus 4 divided by 2 equal minus 3 divided by 2, a negative value, negative number. So in other words, the slope of the tangent at that point is going downwards. In that direction, in the direction of y, the slope is going downward, but in the direction of x, it is going upwards. It is positive. Another concept is the tangent plane equation over a function fxy at a specific point x0, y0. So what would be the equation of that tangent? Z equal fx0, y0, which is the value of f at x0, y0, plus the derivative of f in respect of x at x0, y0 times x minus x0, which gives you the slope in the direction of x, plus the derivative of f in respect of y at point x0, y0, the same point, times y minus y0. Example, fxy equals square root of x squared plus y squared at 3, 4. Let's check the equation of that tangent against this function at this point. So fx xy, let's derive f against x is equal to u prime divided by 2 square root of u. This is how you derive a square root function. So it is 2x divided by 2 square root of x squared plus y squared, which is square root of u. This is the formula. Derived is equal to u prime divided by 2 square root of u. So 2x divided by 2 square root x squared plus y squared equal x divided by square root of x squared plus y squared. Derivation against y, the same thing, is equal to 2y divided by 2 square root x squared plus y squared, or y divided by square root of x squared plus y squared. So z is equal fxy, fx0, y0, you replace 3 and 4 in the first equation, it gives you square root of 25, plus fx x0, y0, so you place 3 and 4 in f of x, which is the derivative of f in respect of x, times x minus x0, which is x minus 3, plus fy x0, y0, so you replace 3 and 4 in the second derivative, then you multiply by y minus y0, which is y minus 4. That is the equation. Okay, then you expand it. 1 over 5, 25 plus 3x minus 9 plus 4y minus 16, which gives you z equal 1/5 of 3x plus 4y. That is the equation of the tangent plane against this function. So again, this is the equation of the tangent plane. It is a plane, not a line, over this function at 3, 4. Another question, let's estimate f 3.1, 3.9. Okay, or z 3.1, 3.9. What would be the height of the plane at this point? Okay, so z 3.1, 3.9 is equal to 1 divided by 5, 3 times 3.1, plus 4 times 3.9. We are replacing x and y in the equation of the tangent plane, which is equal 1/5, 9.3 plus 15.6, around 4.98. Partial derivatives, chain rule for multivariable functions. So let's say we have a function z equal fxy, and x and y are functions of t. So x is equal to xt and y equal yt. The derivative of fxy is dz over dt is equal to dz over dx times dx over dt plus dz over dy times dy over dt. What this means is the derivative for dz against t is equal to the partial derivative of z in respect of x times the partial derivative of x within z in respect of t plus partial derivative of z in respect of y times partial derivative of y within this z against t, or in respect of t. So the generic formula is given by dz over dt equals sum from I equal 1 to n dz partial z divided by partial xi times partial xi divided by partial t, which is like the sum over this equation here, partial z over partial x times partial x over partial t plus partial z over partial y times partial y over partial t, depending on how many variables you have that have a component of x or t rather within them. Okay, so you have x, y, z, w, but all of them are in respect of t. You chain rule them using this method. An example for that, to make it more simple, we have the complex function here, z equal fxy equal x times e to the power of y, and at the same time x equal y squared plus v, y equal y minus v. So find dz over du, or the derivative of z in respect of u. This is equal to dz divided by dx, or partial z over partial x, deriving z in respect of x times the derivative of x in respect of u, plus dz divided by dy times the derivative of y in respect of u. You can try at it yourself, of course. So dz over du is equal to the derivative of fxy in respect of x, which is ey, times derivative of x in respect of u, which is 2u. You multiply them by each other, plus the derivative of z in respect of y, or ey, times the derivative of y in respect of u. Okay, derivative of y in respect of u is equal to 1 times derivative of fxy in respect of y is ey, and x is a constant, so you still keep it within the formula. So dz over du is equal to ey times 2u plus x ey, because the derivative of y in respect of u is 1. Then find dz in respect of dv. It is the same concept. dz over dv is equal to partial z divided by partial x, or derivative of z in respect of x, times derivative of x in respect of v, plus dz over dy, dy over dv. So dz over dv is equal to, at first in respect of x, ey, times derivative of x in respect of v, which is 1, minus y minus, because it is the derivative of z in respect of y, which is EYX, times the derivative of y in respect of v is minus 1. That's why you have minus xey as a component here within this derivative. Breaking it down to smaller pieces to make it even more simple. So to find dz over du, the formula again is dz over dx, or partial z over partial x, almost the same thing, times derivative of x in respect of u, plus partial z partial y times partial y over partial u. dz over dx, or partial z over partial x, is ey. Partial z over partial y is, in respect of y, it is eyx. Partial x over partial u, or the derivative of x in respect of u, is equal to 2u. Derivative of y in respect of u is equal to 1. Then you multiply them together. So you get dz over du is equal to ey times 2u, which is dz dx times dx du, plus dz dy times dy du xey. Partial derivatives, gradient and directional derivatives. So what is the gradient of a function? Gradient of a function fxy is a vector that points in the direction of the maximum or the highest increase of that function. Its magnitude points or refers to the rate of that increase. Gradient for 2D functions is given by nabla f is equal to partial f over partial x, or the derivative of f in respect of x, and derivative of f in respect of y. It gives us also another vector. For 3D functions, the same concept, except we have 3 components, 3 variables. So nabla f is equal to partial f in respect of x, then in respect of y, then partial f in respect of z. So a gradient points to the direction of the highest function increase. The magnitude defines the rate of the change. Gradients are always normal or perpendicular to the level curves or surfaces, as you see here in this representation. This gradient vector changes as the function changes, but is always normal to that function. Example, find the gradient for the function fxy is equal to x squared y plus y to the power of 3. So the gradient is, and you can, by the way, solve it yourself before looking at the solution. So nabla f is equal to partial f divided by partial x and partial f divided by partial y, or the derivative of fxy in respect of x and y next to each other. So the first one is in respect of x, you have 2xy. In respect of y, you have the derivative is x squared plus 3y squared. Evaluate at point 1, 2. So the value for that gradient at 1, 2 is, you fill 1 and 2 in this vector. You get 2 times 1 times 2 and 1 squared plus 3 times 2 squared, which is 13. At 1, 2, the maximum increase of function is given by vector g 13, which is, that's the maximum increase. Okay, that's a specific vector at that point. Another thing to note is that this vector g is normal to the curve at that point, which is 1, 2. Directional derivative. So what is a directional derivative? It defines the rate of change of a function in a specific direction, like that of a vector u. So duf is equal to nabla f dot u. The directional derivative is the dot product between the gradient of a function nabla f and a directional vector i.e. u, which is designated. It measures how much the function is changing in that direction of this vector. Example, fxy is a function equal to xyz plus z squared. V is a vector, 2 minus 1, 2, and P is a specific point, 1 minus 1, 2. These are its coordinates. So what is the derivative of f in the direction of V? You can try to solve it yourself at first. So, at first, nabla f, which is the gradient of this function, is equal to partial f over x, partial f over y, and partial f over z, which is yz plus xz in respect of y plus xy plus 2z in respect of z when we derivate in respect of z. After that, we need to have the dot product with v to get the directional derivative. Okay, so at point P, at first, this gradient is equal to, you replace the coordinates of P in that gradient, 1 minus 1, 2, so you have minus 1 in y and 2, that's minus 2 for x, for xz it is 2, for xy plus 2z, you replace x here in x, then minus 1, then 2, so which is 4 minus 1 or 3. We should normalize the vector v. It needs to become a unitary vector. This is what we're referring to. So v in module or in size is equal to square root of 2 square plus minus 1 square plus 2 square is equal to square root of 9 or 3. So u, the unitary vector of v, is equal to v divided by the length of v, or 1 over 3 times 2 minus 1, 2. Okay, derivative of f in the direction of v, or u rather, the unitary vector of v, is given by nabla f 1 minus 1, 2 is equal to minus 2, 2, 3 on one hand at this specific point, and the unitary vector is 2/3 minus 1 over 3 and 2 divided by 3. So the dot product of both of them gives us the directional vector, the directional derivative. Okay, so nabla f dot u is equal to minus 2, 2, 3 times 2 divided by 3 minus 1 over 3 and 2 over 3 equal minus 4 over 3 minus 2 over 3 plus 6 over 3, which is 0. Conclusion, there is no variation in the direction of that vector and the surface is flat. It's parallel to xy axis. Local maximum and minimum. For a multivariable function fxy or fxyz, a local maximum at a point P is defined by f of P greater than or equal to f of Q for all points Q near P. Okay, so these are the values that are greater than equal to a Q. Okay, for all the points of Q that are, for all the points that are near P, the value of the function is at least equal to f of Q. Okay, it's equal or greater than f of Q. A local minimum is the actual opposite, is defined by fp is less than or equal to f of q for all points q around P. To find the local extrema, which means both the maximum and minimum, we first need to compute the gradient, which gives us the variation or maximum variation at a specific point, and we solve it for nabla f is equal to 0. This gives us the points where the curve is flat. As a reminder at first, the derivative of a function at a point gives us the slope, alright, tan alpha. So when the derivative is 0, it means that the slope is 0. That's why we needed to solve nabla f for 0 to get where the function is flat around a specific point. Alright, after that we should run a second derivative, which is a second derivative test using what is called a Hessian matrix. Note, the second derivative determines the concavity. So in other words, when you have a positive second derivative, it means that the function is concaved upward, so it has a local minima. Just like the illustration to the right. When the function is concaved upward, meaning that it's pointing up, so it has a trough, it has a bottom, or a local minima, which is at this bottom. Meanwhile, if f second, the second derivative, is negative, less than 0, it means that the function is concaved downward. So it has a peak. Okay, why? Because the sides are going down, so it has an upward bump. Okay, because the sides are pointed down. It has a local maxima. The Hessian matrix, it describes the second degree behavior of a curve around a point, whether it's going up or down. It is given by fxx, which is the second derivative of x in respect of x for fx, second derivative of x in respect of y, fyx and fyy. We're gonna understand it further after that. Exercise. Find the local maxima and minima for fxy is equal to x to the power of 3 minus 3xy squared. At first, of course, you can try to solve it yourself before we get into the solution. Nabla f is equal to partial f, or derivative of f in respect of x, and derivative of f in respect of y. So f prime x is equal to, in respect of x, equal to 3x squared minus 3y squared. F prime y is equal to 0, because the derivative of x in respect of y is 0, minus 6xy, okay, because the derivative of y squared is 2y. Now, this is when you start understanding what fxx, fxy, fyx, and fyy mean. So, here you have fxx is the derivative, the second derivative of f prime x, okay, in respect of x. So we are deriving for the second time f prime x in respect of x, which gives us 6x. fxy is the derivative of that same function, okay, which is the first derivative at x, but in respect of y, which is equal to minus 6y. As for f prime y, second derivative in respect of x gives us minus 6y, and second derivative in respect of y gives us minus 6x. Building Hessian matrix. So again, the matrix H, or the Hessian matrix, is given by fxx, fxy, these first two components, and in the second row fyx, fyy. So 6x minus 6y, then minus 6y minus 6x. You get the determinant of this Hessian matrix, and the result is minus 36 times x squared plus y squared. The maximum directional derivative at a point is the magnitude of the gradient in that direction. So max du f is equal to nabla f when it is positive. Okay, the minimum directional derivative at a point is the negative magnitude of that gradient in that direction. As an example, a vector pointed in the opposite direction. So min du f is equal minus nabla f. If nabla f is greater than 0, you have a steep ascent. If nabla f is less than 0, you have a steep descent. Otherwise, if it's equal to 0, it means that the curve is parallel. It is leveled. Going back to the former exercise where we haven't yet found the local maxima and minima for the function fxy. Alright, so nabla f is equal to partial f over x, partial f over y, f prime x, f prime y. We've built the Hessian matrix, which is equal to minus 36 times x squared plus y squared. We need to find where this Hessian matrix is positive, where it is negative. We need to study it. So let's solve for nabla f is equal to 0 to see where f prime x, f prime y are 0 to get the local minima or maxima if possible. So f prime x is equal to 0 and f prime y is equal to 0. So we build a system of equations. You have 3x squared minus 3y squared equal to 0 and minus 6y equal to 0. The critical point, if you solve it, so you have x equals 0 divided by y and y equal 0 divided by x, okay, or minus 6x, which is the same thing. So The critical point, the solution for this problem is x equal 0 and y equals 0. So the critical point is 0, 0. Replacing this point in the Hessian matrix, we get h equal to 0. Why? Because minus 36 times 0, okay? Which behaves like a saddle point. A saddle point is like a level point where there's no going up or down. This is what we mean by saddle. There's no increase or decrease. This means that the test is inconclusive. So again, going back, what we do is get the derivatives of f in respect of x and in respect of y. We solve them for 0 to get the critical point. Then you need to build the Hessian matrix. Actually, you should have already the second derivatives for fx and fy respectively. For fx, you have fxx, fxy. For fy, you have fyx, fyy. You place them within the Hessian matrix. You get the value. Then you replace x and y, if valid, if they were available within the Hessian matrix, by the coordinates of the critical points in order to get how the function is behaving at the second derivative. If it is a saddle point or if it's going up or down. We are checking the concavity, as we mentioned before, because the second derivative gives us the concavity of a function. Another exercise, find the local maxima and minima for fxy is equal to x squared plus y squared minus 4x minus 6y plus 13. Let's start with the first degree derivatives in respect of x and y, which is nabla f. Of course, you can pause the video and try to solve it yourself. So nabla f is equal to partial f divided by partial x, which means derivative of f in respect of x, and partial f to partial y. So f prime x is equal to 2x minus 4. The other parts are 0 because we are deriving in respect of x. F prime y is equal to 2y minus 6. Now let's get the second derivatives. So fxx is equal to derivative of f prime x in respect of x, which is 2. fxy is equal to 0. Then for f prime y, you have f prime y x or fyx is equal to 0 because we have no x here, and fyy is equal to 2. Building the Hessian matrix. H is equal to fxx, fxy, fyx, fyy, first and second row respectively, which is equal to 2, 0, 0, 2. You solve it by same method of the determinant, so it is 2 times 2 minus 0, which is 4. Alright, now that we have both the first and second derivatives, so let's solve nabla f equals 0, or f prime x equals 0 and f prime y equal to 0. F prime x is equal to 0, so 2x minus 4 equals 0, or x equal to 2y minus 6 equal to 0, so y equal to 3. Then the critical point that we've gotten is 2, 3. That's the critical point. Now that we've gotten the critical point 2, 3, the Hessian value, which is 4, positive, and fxx, which is 2, also positive or greater than 0. What can we conclude from that? So as a conclusion, at first, h is equal to 4, greater than 0, and fxx is equal to 2, also greater than 0. So this point, 2, 3, is a local minima. Why? Because the concavity of this curve is positive. fxx gives us that this function is going upward, and since h is greater than 0, so it is an upward concavity along with fxx equal 2, which is also greater than 0. What we can conclude is that 2, 3 is a local minima. Also, since the function is quadratic and unbounded above 2, 3, this is also a global minima as well. Another practice exercise, find the local maxima minima for fxy equal x squared minus xy plus y squared. Again, you can pause the video and try to solve it yourself. Alright, let's continue. So, nabla f is equal to derivative of f in respect of x, then derivative of f in respect of y. Let's start with f prime x. F prime x is equal to 2x minus y. Then we get the second derivatives for fx in respect of x and y, which gives us fxx equal 2 and fxy equal minus 1. F prime y, or derivative in respect of y, is equal to minus x plus 2y, or 2y minus x. Again, the second derivatives for f prime y are fyx in respect of x, which is minus 1, fyy equal to in respect of y. Building the Hessian matrix, so H equal fxx, fxy, fyx, fyy. You simply place them within the matrix. You have 2 minus 1 in the first row and minus 1, 2 in the second row, which gives you 2 times 2 minus 1 times minus 1. So 4 minus 1, which is equal to plus 3, a positive Hessian matrix. Now we have gotten the Hessian matrix and we have already the first derivatives for the function by nabla f prime x and f prime y. Let's solve for 0, both f prime x and f prime y, to get the critical point, the coordinates of the critical point for that function. Solving nabla f equals 0, you have 2x minus y equals 0 and 2y minus x equals 0. 2y equal plus x, you replace the value of x in the first equation, so you get 2y minus y equal to 0. Then y equals 0 and x equals 0, that's the critical point. So given that we have xx is equal to 2, which is positive, 0, 0 is the critical point, and the Hessian matrix is also positive, which is plus 3 greater than 0. So fxx is greater than 0, the discriminant, which is actually the determinant of the Hessian matrix, which is 3, greater than 0, then 0, 0 is a local minima. Here's a refresher on how we analyze what a point is. If d, which is the determinant or the discriminant for the Hessian matrix, if it's greater than 0, and the second derivative over x, which is fxx, is greater than 0, you have a local minimum or minima. If d greater than 0 and fxx is less than 0, you have a local maximum. The concavity is going downward. If d less than 0, then you have a saddle point, meaning you have a leveled curvature. There's no up or down. If d equals 0, then the test is inconclusive. We cannot know. Another one, find the local maxima and minima for fxy equal x to the power of 3 plus y3 minus 3x minus 3y. Of course, you can pause the video and try to solve it yourself. Nabla f is equal to partial f over x, partial f over y. Let's find the first derivatives in respect of x and y. F prime x is equal to 3x2 minus 3. Then f prime y is equal to 3y squared minus 3 as well. Then the second derivatives, fxx is equal to 6x, fxy is equal to 0 because we don't have any y component in this derivative. Then fyx is equal to 0, fyy is equal to 6y. Building the Hessian matrix, H equal fxx, fxy, fyx, fyy. So you place this one in the first row and the second one or second set in the second row. Equal 6x, 0, 0, 6y, which gives us 36xy. Let's solve for nabla f is equal to 0, which means f prime x equals 0 and f prime y equal 0. Let's place them in a system of equations. So 3x squared minus 3 equal 0, 3y squared minus 3 equal 0. Then 3x squared equals 3, so x squared equal 1, and y squared equal to 1. In other words, x is equal to plus minus 1. That's the square root. And y is equal to plus minus 1. And here you don't have only one critical point, but rather multiple critical points, which are the combinations of plus minus 1 for x and plus minus 1 for y. So the Hessian matrix is equal to 36xy. That's the discriminant rather, which is the determinant of the Hessian matrix. Fxx equals 6x. Critical points gave us plus minus 1 at x, plus minus 1 at y. You combine them together, you get all the combinations possible. The critical points are minus 1, 1, 1 minus 1, minus 1 minus 1, and 1, 1. These are all the critical points possible. We need to check for these points what's happening to the curve. Each critical point is a case of its own. In order to solve it, you place x and y of that critical point within the Hessian matrix, or the discriminant rather, and within fxx. So for minus 1, 1, discriminant h is d equal minus 36. Okay, 36 times minus 1 times 1. It is less than 0, so it is a saddle point. There's no maximum or minimum. For 1 minus 1, d is equal also to minus 36, so it is a saddle point. For minus 1 minus 1, h equal plus 36 greater than 0, and fxx is equal to minus 6, which is less than 0, so minus 1 minus 1 is a local maximum. As for 1, 1, discriminant is d equal plus 36 greater than 0, and fxx is greater than 0, then 1, 1 is a local minimum. A new section, multiple integrals. In this section, we're going to talk about double integrals, triple integrals, and much more. So let's start with it. At first, double integral over a rectangular region. So the double integral is defined by fxy, small fxy, is equal to double integral over r of fxy dA, where dA is the differential of the region, or rather it is dy times dx, which gives you the area of that small section, of that small square, if you will. Now, if we sum it up over the entire region, you get the entire area of that region when fxy is equal to 1. So this integral for fxy greater than 0 represents the accumulated volume, because we are multiplying the surface, the area, with the height of that function. So it represents the volume underneath the curve, or surface in a specific region, dA. Recap: the integral of fx dx is the accumulated area under fx as a curve. That's the first degree integral, where each area is equal to fx times delta x. That's delta x, that's fx, so it is the area of that rectangle, almost equal to the area under the curve within this parcel, or within this slice. The double integral over a region R of fxy dA is the accumulated volume, where dA is the area underneath the function fxy, multiplied by the height of the curve fxy. It gives us back the volume, just like you see on the right down picture here. So you have delta x, delta y, or dx dy, which is dA, multiplied by the height of the curve. It gives you the volume of the curve in that region. Of course, as you sum it up, as you integrate it throughout the region, you get the entire volume underneath the curve. How to solve a double integral of a function over a region R? Let's consider that our region is bounded by the following constraints. You have x is between a and b, and y is between c and d. So I is equal to the double integral over region R fxy dA, equal integral from c to d, then integral from a to b, c to d are the constraints of y, then integral from a to b, which are the constraints of x, fxy dx dy. Notice something, that we place the x first. Why? Because we are solving first in respect of x, which is between a and b. Then the solution, you place it back in the integral and you solve it in respect of y, between c and d, which is equal to integral from a to b, c and d, fxy dy dx. According to Fubini, it's completely valid to switch the order of integration dx dy versus dy dx. But let's say you choose dx dy, you solve the integral for dx first, considering y as a constant. Then you solve it in respect of y. To make it clearer, this is the evaluation point. Let's say you have the double integral over a region R of x plus y dA. At first, we need to define what is the region. The region is where x is greater than 0, less than 1, so x is between 0 and 1, and y is between 0 and 2. So we start with dx or dy. Let's start with dx at first. It is integral from 0 to 2, the boundaries of y, of integral from 0 to 1, boundaries of x, x plus y dx. You solve for x first, then you solve it for dy, which is equal, of course, we treat y as a constant in such case, and we integrate in respect of x. So integral from 0 to 1, x plus y dx is equal to x2 over 2 plus yx between 1 and 0. These are the boundaries, is equal to 1/2 plus y. Why? Because as you place 1 in x, you get 1 over 2 plus y. Minus 0, because if you place 0 back in x, you get all zeros. So the answer, you place it back in the integral, then you integrate in respect of y or dy. The answer is 1/2 plus y for the integration in respect of x. You place it back in the equation, or in the integral rather. You get integral from 0 to 2. 1/2 plus y dy is equal to y over 2 plus y squared divided by 2 between 2 and 0, which is equal to fb minus fa. You place 2 at first within y. It is equal to 2 divided by 2 plus 4 divided by 2 minus 0 divided by 2 plus 0 divided by 2 within parentheses, which is equal 1 plus 2 or 3. That's the final answer. Double integral over a generalized region. A region R is not always necessarily defined by simple boundaries or rectangular boundaries. It can also be a set of curves or a triangle. In this case, we try to define the limits of x and y and whether we should convert the variables to a different set of coordinates, such as polar coordinates. Let's say you have a region R where x and y bounded in this following manner. So y is between c and d, specific values, but x is bounded by two functions, h1 of y and h2 of y. Then in order to solve this integral, I is equal to integral from c to d, then integral of fxy from h1y to h2y dx dy. We solve in respect of x, you get a function of y, that's why it is placed in the middle. You solve it first, then you solve that in respect of dy. So you get something that has y within it, then you integrate in respect of y to get the integral from c to d in respect of y. We integrate in respect of x first, then in respect of y, since its bound are real values. To get a clearer picture and understand it further, we're gonna practice with a typical exercise. So let's say we want to compute the area of the region bounded by the parabola y equal x squared and the line y equal 2x. At first, we need to get the boundaries for that integral. So we need to know where these two curves, which is a parabola and a line, intersect. We try at first to draw these two curves. We plot them on system of axes, and we need to check at which points they intersect. You have y equal x squared, y equal 2x, then you place y equal y, then x squared is equal to 2x to see at which values of y these curves cut each other. So you get x squared minus 2x equal to 0. So x times x minus 2 is equal to 0. The boundaries are then at the x-axis, x equals 0 and x equal 2. These are the x boundaries. As for the y boundaries, y is simply bounded between the lower function and the upper function, which is y equal x squared and y equal 2x. These are the y boundaries. So y equal 2x on top and y equal x squared at the bottom. Let's get the square integral. And at first, here we don't have a function, we're only computing the integral of a region or the area of a region, which gives us back the area of that region without the volume. So when you add the function fxy to the integral, you are adding the height to a surface. In such case, you get the volume instead. We first integrate in respect of y to get rid of x. Then we integrate in respect of x, for which we have a numerical value for boundaries. Okay, so a equal integral from 0 to 2, then integral from x squared to x dy. Okay, we solve dy first, then we integrate in respect of x to get real values. You need to note here, and this is how you know it, x has specific discrete values from 0 to 2. So you solve the x last, but y is changing from y equal x2 to y equal 2x. That's why you solve that integral first in respect of dy, then you solve it in respect of the x to get the final value of the integral, which is the area of that region. A equal integral from 0 to 2, then integral from x squared to 2x dy dx. So a equal integral from 0 to 2 of the result of integral from x squared to 2x dy, which is equal to y between 2x and x squared dx. Integral from 0 to 2x minus x squared dx, which is equal to 2x squared divided by 2 minus x3 divided by 3 between 2 and 0, which is equal to 4 minus 2 to the power of 3 divided by 3, which is 4 minus 8 over 3. For the second bound, it is 0. If you place 0 back here, you get nothing. Okay, it is 0. So the final result is 4 divided by 3. Double integral and polar coordinates. So when dealing with a curved region, such as a circle, it is often hard to describe and to solve using xy. You need to transition to another type of coordinates, which are no longer Cartesian coordinates. That's why we have to move to polar coordinates. In such case, by converting the system from xy, the Cartesian coordinates, to r theta, or polar coordinates, where r is the radius and theta is the angle. Consider a circular region with the equation x squared plus y squared equal 9. The radius r varies from 0, which is the center of the circle, up to 3, because r squared is equal 9, then r equal to 3. And theta, the angle, varies from 0 up to 2 pi, which is a complete rotation, giving you the full area of the circle, if you will. How to transition into polar coordinates from a Cartesian xy system? At first, we need to establish the relationship between xy and r theta. If we look at this illustration here, we have a unit circle. So what is the relationship between r theta and x and y? For theta, if you look at theta here, cosine theta is equal to adjacent side divided by the hypotenuse, which is r, which is equal to x over r. So x equal r cosine theta. As for sine theta is equal to the opposite side, which is y, the height, divided by the radius of the circle. So y is equal to r sine theta. We got the values of x and y in respect of r and theta. Now we need to get the x dy transform into the r d theta. This is what is called the Jacobian of the transformation from xy coordinates to r theta coordinates. The j is equal to dx over dr, dx over d theta. We are deriving x and y in respect of r and theta, respectively. So j equal dx over dr, dx over d theta in the first row, then dy over dr, dy over d theta in the second row, which is equal to, in respect of r, for x, it is cosine theta, then in respect of theta, it is minus r sine theta. For the second, in respect of r, it gives us sine theta, in respect of theta, it gives us r cosine theta. Then you evaluate the determinant, which is equal to r cosine squared theta. Minus minus is plus, plus r sine squared theta, which is equal to r times cosine squared theta plus sine squared theta equal to r. That is the Jacobian of the transformation. Hence, dx dy is equal to r dr d theta, the outcome of the transformation. Example, find the area of a circle with a radius r equal 2. Let's use the double integral to find that area. At first, the radius vary from r equals 0 towards r equal 2, which is the maximum boundary of the disk ratio. Theta varies from theta equals 0 up to theta equal to pi rotating clockwise to complete a full circle, which is a complete rotation around the center. A equal double integral over the region r dx dy. Here we need to change the variables, to change the coordinates. Of course, dx dy converts to r dr d theta as we've seen previously. A equal integral from 0 to 2 pi d theta, integral from 0 to 2 r dr. We need to integrate in respect of r, then in respect of theta. So it is equal to integral from 0 to 2 pi, integral from 0 to 2 r dr, which gives us r squared over 2 between 2 and 0, which is equal to 4 divided by 2. Now this is a constant, we can multiply it outside of the integral. Integral from 0 to 2 pi d theta, which gives us 4 divided by 2 is 2 times theta between 2 pi and 0, which is pi times r squared. If you apply the formula that we already know about the area of the circle, it gives us the same value. This is how you can get this area. Another example, evaluate the double integral for the following function where r is the upper half of the disk of radius 3 centered at the origin. Now mind you, before we evaluated only the area, so this function fxy was equal to 1. It did not exist. Here in this case, you are evaluating the double integral of this function over that area, where the area is the upper half of the disk of radius 3, so which gives you the volume, no longer only the surface. At first, where r is the upper half of the disk of radius 3. So upper half of the disk, it means that theta is going from 0 to pi. It's no longer rotating the entire circle. And the radius is 3, so it is traveling from 0 to 3. This would be the illustration of that region. So theta is between 0 and pi, and the radius is from 0 to r equal 3. Region r is from 0 to 3, and theta is between 0 and pi. X equal r cosine theta, y equal r sine theta, and j, which is dx dy, becomes r dr d theta. I equal integral from 0 to pi, integral from 0 to 3 of square root r squared cosine squared theta plus r squared sine squared theta, r dr d theta. As you know, cosine squared theta plus sine squared theta equal to 1. Okay, so you get r squared to the outside, and you multiply by cosine squared theta plus sine squared theta, which gives you 1. You are left with the square root of r squared, which is r. So I equal integral from 0 to pi, integral from 0 to 3, r squared dr d theta. At first you solve in respect of r, then in respect of theta. So it is equal integral from 0 to pi, r to the power of 3 divided by 3, from 3 to 0 d theta, which is equal to 3 to the power of 3 is 9 times theta between pi and 0, which is 9 pi. Another exercise to sharpen our understanding about double integrals. I equal double integral over region r of x squared plus y squared dA, where r is the region inside the circle r equal 2 cosine theta, and outside the circle r equal 1. Since we are working with circles, we need to convert to polar coordinates, because the region itself is a set of circles. But in order to understand or to know the boundaries, we need to plot the region on a graph to see how r and theta are changing. This is the visualization of r equal 1 and r equal 2 cosine theta. We have two circles, the first one having a radius of 1, starting from the origin or centered by the origin of the axis. The other one as well has a radius of 1, except it is shifted by 2 squares to the right. How they intersect? We need to find the angles at which they intersect together. For r, we already know that r is changing between two functions, which are 2 cosine theta and r equal 1. But how is theta itself changing? You simply place r equal r, or 1 equal 2 cosine theta which means cosine theta is equal 1/2. Then theta is equal to r cosine 1/2 equal to pi over 3 or 60 degrees. So the angle is changing between minus pi over 3 to plus pi over 3. So the region R is given by R changing from 1 to 2 cosine theta and theta changing from minus pi over 3 to plus pi over 3. Then I equal integral from minus pi over 3 to plus pi over 3, integral from 1 to 2 cosine theta of x squared plus y squared, which is r squared cosine squared theta. We moved into the polar coordinates, plus y equal r sine theta, which is equal to r squared times sine squared theta, times dA is r dr d theta, using the Jacobian, which is r. So r squared times cosine squared theta plus sine squared theta, you get rid of cosine squared theta plus sine squared theta, which is 1, equal to integral from minus pi over 3 to plus pi over 3 on the outside, integral from 1 to 2 cosine theta, r to the power of 3 dr d theta. Integral from minus pi over 3 to plus pi over 3, then from 1 to 2 cosine theta, r to the power of 3 dr d theta. Alright, then I equal integral from minus pi over 3 to plus pi over 3 of r4 divided by 4 between 2 cosine theta and 1, which gives you 16 cosine 4 theta divided by 4 minus 1 divided by 4. Okay, equal to integral from minus pi over 3 to plus pi over 3, 4 cosine 4 to the power of 4 theta minus 1 4 d theta. Now, mind you that cosine square theta in the rules of trigonometry, you can get from it 1/2 cosine 2 theta plus 1. Why? Because cosine a plus b equal cosine a cosine b minus sine a sine b, cosine a minus b equal cosine a cosine b plus sine a sine b. We're gonna see them again later. Cosine to the power of 4 theta is equal to 1/4 cosine square 2 theta, which is, by the way, cosine square theta times cosine square theta, which is 1/2 cosine 2 theta plus 1 square. It gets you 1/4 cosine square 2 theta plus 2 cosine 2 theta plus 1. As a recap on the trigonometric functions, this is how we got the equivalence that we've gotten in the previous slide. So cosine a plus b is equal to cosine a cosine b minus sine a sine b. Cosine a minus b is equal to cosine a cosine b plus sine a sine b. We add these two equations together from the left of the equivalence to the right, so you get 2 cosine a cosine b, these two arguments. By the way, minus sine a sine b plus sine a sine b would cancel out, okay, when you add the two equations, because this minus this, they are equal, so they beget you 0. So 2 cosine a cosine b is equal to 1, which is cosine a minus b when a equal b, or cosine 0, plus cosine a plus b. So cosine a cosine b is equal to 1/2 1 plus cosine a plus b when a equal b equal theta. Cosine square theta is equal 1/2 times 1 plus cosine 2 theta. The same thing for sine square theta. So sine square theta is equal to 1/2 times 1 minus cosine 2 theta. By adding the two equations, but instead of adding them immediately, you need to multiply one of them by minus so that they won't cancel out sine a sine b. Okay, instead, one of these equations would cancel out cosine a cosine b. You get rid of it, and all you're left with is 1 minus cosine 2 theta divided by 2. Going back to our integral, so I equal integral from minus pi over 3 to plus pi over 3, 16 over 4, which gives us 4 cosine to the power of 4 theta minus 1/4 d theta. As a reminder, cosine square theta is equal to 1/2 1 plus cosine 2 theta. Here you have cosine to the power of 4, meaning that cosine square theta times cosine square theta. So how do we deal with this type of integral? Okay, cosine square theta again is equal to 1/2 1 plus cosine 2 theta, then cosine 4th theta is equal to cosine square times cosine square, or 1/2 times 1/2, or 1 divided by 4, times 1 plus cosine 2 theta square, which gives us 1/4 cosine square 2 theta plus 2 cosine 2 theta plus 1. Again, you have another square for 2 theta, so we need also to break it down. Cosine square 2 theta is equal to 1/2 cosine 4 theta plus 1. You place it back in the first equation. Cosine 4 theta is equal to 1/4 times 1/2 cosine 4 theta plus 1. We simply placed it back in this equation, plus 2 cosine 2 theta plus 1. So I is equal integral from minus pi over 3 to plus pi over 3, 1/2 cosine 4 theta plus 1/2 plus 2 cosine 2 theta plus 1 minus 1/4 d theta. So we simplify I, you get integral from minus pi over 3 to pi over 3, 1/2 cosine 4 theta plus 2 cosine 2 theta plus 5 over 4 d theta, which is equal to sine 4 theta divided by 8 plus sine 2 theta plus 5 divided by 4 theta between plus pi over 3 to minus pi over 3, which is equal to minus square root of 3 divided by 8 plus square root of 3 plus 10 divided by 12 pi, or 7/3 square root of 3 plus 5 6 pi. Another practice exercise, I equal double integral over region R of r square cosine square theta dA, where r is the first quarter of the circle x squared plus y squared equal 4. Let's at first draw the region. So we have the quarter of a circle, then r travels between 0 and 2, and theta between 0 and pi over 2, because we only have the first quarter of the circle as a region. Okay, now how to solve cosine square theta d theta? Going back to trigonometry and trigonometric laws or rules, you have cosine a plus b is equal to cosine a cosine b minus sine a sine b. Cosine a minus b is equal to cosine a cosine b plus sine a sine b. By the way, you need to memorize that for the cosine, plus becomes minus and minus becomes plus, and on the other side of the equation you multiply the cosines together and the sines together. So if we add 1 and 2, the first and second equation, from left to right, by the way, suppose that a is equal to b, because here cosine square theta, cosine a is equal cosine b. You have a square. Then cosine a minus a, which is cosine 0, plus cosine 2a is equal to 2 cosine a cosine a. We have added these two together, or 2 cosine square a. Okay, now the minus and plus for the sine cancels out, so this one is removed. Then cosine square a is equal 1/2 times 1 plus cosine 2a. I is equal 4 integral from 0 to pi over 2, and we use this transformation, 1/2 times 1 plus cosine 2 theta d theta. Then you multiply 1/2. You move it to the outside of the integral, multiplying it by 4. So I is equal 2 times theta plus 1/2 sine 2 theta, which is the integral of cosine 2 theta between pi over 2 and 0, which is equal to 2 times pi over 2 plus 1/2 sine pi, which is 0, minus 0, which is equal to pi. A new exercise, I equal double integral of r divided by 1 plus r squared dA, where the region R is the disk of radius 3, given by x squared plus y squared equal to 9. Let's draw the region. So the region is simple. It is a disk. Then the radius goes from 0 to 3, which is the maximum outside bound, and theta goes from 0 to 2 pi, a full rotation around the disk. Then r belongs to of lowercase r, which is the radius from 0 to 3, theta between 0 and 2 pi, and dA is equal to r dr d theta, which is the transformation into polar coordinates. I is equal to integral from 0 to 2 pi integral from 0 to 3, r squared divided by 1 plus r squared dr d theta. Why? Because we multiplied by r, which is on the outside, which is the Jacobian. Let's break it down. So the integral, for simplicity, looks like this. This one is I1, integral from 0 to 3, r squared divided by 1 plus r squared dr. We will solve this one at first, then we will place it back in I. I1 is integral from 0 to 3 of r squared divided by 1 plus r squared dr, which can be broken down into 1 minus 1 divided by 1 plus r squared dr. The integration of the first one gives us r, but the second should be familiar. If you go back to trigonometric identities, the integral of 1 divided by 1 plus r squared gives us tan to the power of minus 1, or arctan of r. The integral becomes r minus tan to the power minus 1 r between 3 and 0, or 3 minus tan minus 1, 3. We place it back into I. So I equal integral from 0 to 2 pi 3 minus tan to the power minus 1, 3 d theta, which is equal to 3 minus tan to the power minus 1, 3 times theta between 2 pi and 0, equal 2 pi times 3 minus tan minus 1, 3, which is the final answer for this integral. Area, mass, and center of mass. So how we can get these three parameters from a double integral? Let's say the area of a region is given by, the region is actually R. So the area is equal to double integral R1 dA. Again, as we mentioned before, this is when the function fxy is equal to 1. So what you're getting from the integral instead of the volume is actually the area of that region. As for the mass is the product of a density function with the volume. So m is equal to rho times v. So when we have a density function over an area, although it's not a volume, but you can consider it as a thin sheet of paper, we can get the mass by multiplying rho xy by dA and integrating over the region. So instead of a volume with a density, it is a surface with a density. Whatever gets a density function becomes massive. It gets weight, so you can evaluate its mass. It applies also to surfaces and areas. An example for that, find the area of the region bounded by y equal x squared and y equal x. A equal to double integral r of 1 times dA, where dA of course is r dr d theta, since we have polar coordinates, since we have curves. So this is the representation. Y equal x squared is below and y equal x is above, and the region is this one, bounded by both curves. The intersection between y equal x and y equal x squared is equal to, replace y equal y, so x squared is equal to x, then x2 minus x is equal to 0, so x times x minus 1 is equal to 0. The boundary for x is then the one from 0 to 1, x from 0 to 1. As for y, it is bounded between y equal x squared and y equal x. A equal integral from 0 to 1, integral from x squared to x dy dx, which is equal to integral from 0 to 1 y between x to x squared dx, which is equal integral from 0 to 1 x minus x squared dx. No need to transfer to polar coordinates. Then I is equal x squared divided by 2 minus x3 divided by 3, the integration of this term between 1 and 0, which is equal to 1, 6. Let's say the same area has a density function rho xy is equal to x plus y. Find its mass m. M is equal to integral from 0 to 1, integral from x squared to x, x plus y dy dx. It is equal to integral from 0 to 1. We've integrated in respect of y, which gives us xy plus y squared divided by 2 between x and x squared dx is equal to integral from 0 to 1 x squared plus x2 divided by 2, which is replacing y by x here, minus x3 plus x4 divided by 2, replacing x squared into I in the second branch of the integral. equal integral from 0 to 1 x squared plus x2 divided by 2 minus x3 minus x4 divided by 2 dx equal x3 divided by 3 plus x3 divided by 6 minus x4 divided by 4 minus x5 divided by 10 between 1 and 0. The total of 1/3 plus 1/6 minus 1/4 minus 1 over 10 gives us 3 over 20, which is the mass of the solid. Center of mass. The center of mass coordinates, or the center of gravity, are given by the following. X bar is equal to 1 divided by m double integral over region R x rho xy dA, which is the average, or the point where the average of the mass is located. Y bar is equal 1 divided by m double integral R y rho xy dA. Going back to the former example, m is equal to 3 divided by 20. Let's find double integral R x rho xy dA. So I is equal to integral from 0 to 1, integral from x squared to x times x plus y dy dx. I equal integral from 0 to 1, integral from x squared to x times x plus y dy dx is equal to 0, 1, x2 to x of x squared plus xy dy dx equal to integral from 0 to 1 x squared y plus x y squared divided by 2 between x and x squared, which is equal to integral from 0 to 1 x3 plus x3 divided by 2 minus x4 plus x5 divided by 2 in parentheses equal x4 by 4 plus x4 divided by 8 minus x5 divided by 5 minus x6 divided by 6 times 2, which is 12, equal 11 over 120. Now let's find the center of gravity, x coordinate. It is equal to 1 over m times 11 divided by 120, which is 20 divided by 3 times 11 over 120, or 11 over 18. Let's find now the y coordinate for the center of gravity. So at first we will start by the double integral over r of y rho xy dA. Then we divide by the mass m. I equal integral from 0 to 1, integral from x squared to x, yx plus y squared dy dx. We multiplied by y, which is equal to x y squared divided by 2 plus y to the power of 3 divided by 3 between x and x squared, integral from 0 to 1 dx. We replace by x, then by x squared, so it gives us integral from 0 to 1 x3 divided by 2 plus x3 divided by 3 minus x5, which is x4 times x divided by 2, minus x6 divided by 3. After that, equal x4 over 8 plus x4 over 12 minus x6 divided by 12 minus x7 divided by 21 from 1 to 0, which is 13 over 168. Then y bar is equal 1 divided by m times 13 over 168, or 20 divided by 3 times 13 over 168, which gives us 65 divided by 126. That's the y coordinate for the center of gravity. Triple integrals. A new section within the multiple variable integrals, or multiple integrals for a multivariable function. A triple integral computes a cumulative quantity of a function fxy in a 3D volumetric region E in space. So I is equal triple integral in a region E of xyz times dv. If xyz is equal to 1, then the integral computes simply the volume of the region E. Just like in the double integral, it computes the area. If fxyz represents the density function rho, then the integral result becomes the mass of the solid, which is m is equal to rho times v, or m is equal to triple integral E fxyz times dv. A triple integral is described as the sum of sums, or integration of multiple integrals together, each one adding up a cumulative quantity in one dimension or over one axis. Let's consider a 3D region with the following constraints: x varying between 0 and 2, and y varying between 0 and 3, which is almost a cube. And z varies between 1 and a plane z equal to y. So this cube is slashed on top by z equal to y equation. So I is equal to triple integral over region E fxyz dv, integral from 0 to 2, then from 0 to 3, then from 1 to 2y, fxyz dz dy dx. At first, integrate in respect of z. Why? Because it is z that is changing from one discrete value to actually a function, which is 2y. Then in respect of dy, then in respect of dx to solve the integral. How to solve? You divide and conquer by breaking it down to 3, then solve one integral after the other. So you have I equal triple integral in region E fxyz dv equal integral from 0 to 2, 0 to 3, integral of 1 to 2y fxyz dz, which you start with first. Okay, you solve first in respect of dz between 1 and 2y. Then, once you get the result, you solve it in respect of dy between 0 and 3. After that, you place it back in the integral and solve it in respect of dx between 0 and 2. And finally, you get your final answer, which is I equal fx. Example, supposing fxyz is equal to 1, we only want to evaluate the volume in such case for a boxed region defined by E, where x, y, z are like this. X is between 0 and 2, y is between 0 and 3, and z is between 0 and 4. So we want to get I equal triple integral over region E fxyz dv. So I is equal to integral from 0 to 4 for dz, integral from 0 to 3 for dy, and from 0 to 2 for dx, which is equal to integral from 0 to 4, integral from 0 to 3, x between 2 and 0. So we started with x, okay? Integral of 1 in respect of dx is x between 2 and 0, dy dz is equal to integral from 0 to 4, 0 to 3, 2 times dy dx, equal 2 dy dx becomes 2y. That's the integral from 3 to 0 for the boundaries of y, which gives you integral from 0 to 4 on the outside of 6 dz, which is the final boundary, is equal to 6z from 0 to 4 equal 24, which is the volume of a 3D rectangular box of length 2, width 3, and height 4. Exercise. Evaluate the following integral for the region limited by cylinder of base x squared plus y squared equal 4 and z equals 0, and the plane z is equal to x plus y. Of course, you can pause the video and try to solve it yourself. At first, we need to define the region E. This region is given by x squared plus y squared equal 4, which is the projection on xy plane of the cylinder. So x squared plus y squared equal 4 is the circle of the cylinder, or this is the section of the cylinder on the xy axis. As for the height of the cylinder is limited by z is equal to 0 and z is equal to x plus y, which is a plane slashing the cylinder on top. So these are the boundaries. We need to convert to cylindrical coordinates in order to work this example, which means you need the circular or polar coordinates for x squared plus y squared is equal to 4. As for z, it remains z. So r is between 0 and 2, theta is between 0 and 2 pi because it is the entire circle or disk, and z is between 0 and x plus y, which is the equation of a plane slashing or cutting the cylinder on top. Cylindrical coordinates are the following: x equal r cosine theta, y equal r sine theta, and z is equal to z. Z remains the same. I equal integral from 0 to pi, integral from 0 to, which is the radius, and then integral from 0 to x plus y z times r dz dr d theta. R dr d theta are the transformation to the polar coordinates. Again, theta is between 0 and 2 pi, radius from 0 to 2, and z is between 0 height up to the plane x plus y. So I equal integral from 0 to 2 pi, integral from 0 to 2 of z squared divided by 2 between x plus y and 0, which is equal 1/2 integral from 0 to 2 pi, from 0 up to 2, x squared plus y squared plus 2xy, which is x plus y squared, r d theta, equal 1/2 integral from 0 to 2 pi, from 0 up to 2, r squared, x squared is equal to r squared cosine squared theta, y squared is r squared sine squared theta. So both together give you r squared, because cosine squared theta plus sine squared theta is equal to 1, plus 2r squared cosine theta sine theta. Integral from 1 over 2, 0 to pi, 0 to, you multiply this r on the inside, don't forget about it. We integrate in respect of r, it gives you 1/2 integral from 0 to pi, r to the power of 4 divided by 4 plus 2r4 divided by 4, which gives you r4 divided by 2 cosine theta sine theta between 2 and 0, equal 1/2 integral from 0 to 2 pi, 4 plus 8 cosine theta sine theta d theta. Okay, how to solve that? Trigonometric identities. So you have sine a plus b equals sine a cosine b plus cosine a sine b. Sine a minus b is equal to sine a cosine b minus cosine a sine b. When we add the two together, you get sine 2a, if a is equal to b, is equal to 2 sine a cosine b, because sine 0 is equal to 0. So cosine a sine a is equal to 1/2 sine 2a. So I is equal to integral from 0 to 2 pi, 1 plus 2 cosine theta sine theta d theta, equal to integral from 0 to 2 pi, 1 plus sine 2 theta d theta. That we can solve. Equal to times theta minus 1/2 cosine 2 theta between 2 pi and 0, equal to times 2 pi minus 1/2 minus 0 plus 1/2 is equal to 4 pi. Integrals or triple integrals over general regions. So for cylindrical solids, the transition to r theta z. For spherical solids, the transition would be to rho, theta, and phi, where theta is the angle that is changing on the xy horizontal plane, and phi is the angle changing on the vertical plane. So given this sphere, you notice that actually it is inverted here. So theta should be between x and y, and phi between x and z. The volume of the cylinder is the area of the lower or upper disk multiplied by the height z, but for a sphere it changes. So for spherical solids, we need to transition to rho, theta, and phi. How to get the volume V of a sphere? If we integrate rho from 0 to r, you get the length of the radius, okay, which is the length of this segment. Then we rotate it from 0 to pi over phi, which is 0 to pi. So you have this half disk on the vertical plane. After that, we rotate it by 2 pi. So let's say you rotate it by 2 pi around the y-axis. Imagine it. And as it rotates, it is smudging. It is dripping ink. So what it forms is a sphere. And when we integrate these three components like this, you get the volume of the sphere. Example, volume of a sphere of radius r. So in such case, rho is between 0 and r. Theta is between 0 and 2 pi, which is the horizontal angle. And phi is between 0 and pi. So I is equal triple integral over region E, fxyz dv, and fxyz is equal to 1. Here we are only evaluating the volume of the region. So we should switch to spherical coordinates. Now the Jacobian of the transformation, which we will see later how we got it, is j is equal to rho squared sine phi. I is equal integral from 0 to pi, which is over phi, integral from 0 to 2 pi over theta, and integral from 0 to r, rho squared sine phi. Jacobian of the transformation, d rho, d theta, and d phi. Then let's at first evaluate in respect of r, or rho rather. Integral from 0 to r, rho squared sine phi d rho equal rho 3 over 3 sine phi between r and 0 equal radius to the power of 3 divided by 3 sine phi. Then I theta in respect of theta equal to r3 divided by 3 sine phi. This is regarded as a constant, so you move it outside of the integral. Integral from 0 to 2 pi d theta is equal to r3 divided by 3 sine phi times theta between 2 pi and 0. So it is equal to 2 pi r3 divided by 3 sine phi equal 2 pi r3 divided by 3. All of these are constant, so you move them outside of the integral. Integral from 0 to pi sine phi d phi equal 2 pi r3 divided by 3. Integral of sine phi is minus cosine phi between pi and 0 equal 2 pi r3 divided by 3 times 1, because cosine pi is minus 1 times minus is plus 1, minus minus 1, cosine 0 is 1, so 2 times 2 pi r3 divided by 3, which is 4/3 pi r3. That is exactly the formula to get the volume of a sphere. How do we get xyz in relation to rho phi theta, and j the Jacobian of the transformation into spherical coordinates? We note at first that theta is the angle changing over the horizontal xy plane and phi is changing on the vertical plane. H is the vertical projection of rho over the xy plane, as you see in the picture, and V is the projection, or if you want the intersection of rho with the sphere, you project that point down to the xy plane. This is what V looks like. This is the definition of V. It is an arbitrary dimension or segment that we've taken in order to facilitate to find the values of x and y in respect of rho, phi, and theta. Also, the value of z. Sine phi is equal to opposite side divided by the hypotenuse. So h equal rho sine phi. Okay? Opposite side is h as you see it, and hypotenuse is rho. So sine phi is equal h over rho, then h equal rho sine phi. Cosine theta, this one is equal to x over the hypotenuse, which is h. So we replace the value of h, x equal rho sine phi cosine theta. Then sine theta is equal to y divided by h. So y equal h times sine theta, which is rho sine phi times sine theta. Finally, cosine phi is equal to z divided by rho, then z equal rho cosine phi. After we've gotten x, y, and z, let's find the Jacobian of the transformation into spherical coordinates. So j is equal to the partial derivative of x in respect of rho, then in respect of theta, then in respect of phi, that of y in respect of rho, theta, phi, and z respectively, okay, one after the other. Derivative of z in respect of rho, in respect of theta, and then in respect of phi, and we find the determinant for this matrix, which is the Jacobian of the transformation. So you replace the partial derivative of x in respect of rho is sine phi's cosine theta, then in respect of theta, minus rho sine phi sine theta, in respect of phi, plus rho cosine phi cosine theta. The same thing for y. So in respect of rho, sine phi sine theta, in respect of theta, rho sine phi cosine theta, in respect of phi, rho cosine phi sine theta. And finally for z, in respect of rho cosine phi, for theta 0, and for phi minus sine phi. You evaluate to find the determinant, which gets you rho square sine phi. That is the Jacobian of the transformation into spherical coordinates. Vector calculus and vector fields. Another new section which will go into vectors, parametric surfaces, and surface integral. What is a vector field? A vector field assigns a vector for each point in space throughout the domain where the function exists. So in 2D, fxy is equal to mxy I plus nxyj, where I and j of course are the unitary vectors. In 3D, fxyz is equal to mxyz I plus nxyz j plus pxyz k. I, j, k are respectively for xyz axis. At each point xyz, there's a vector. F is the field or the set of all the vectors within this region. Gradient of a vector. We've probably seen that in previous lessons, but we're gonna recap on it. So what is a gradient? The gradient points to the direction of the greatest increase in a function. Its magnitude represents the rate of that increase. Okay, so it is represented by nabla f, which is the partial derivative of the function f in respect of x, and partial derivative of f in respect of y. What are the different types of operations for vectors? Okay, so vector operations are divergence, which measures how much a vector field spreads from a source or sink point. Curl, which measures how much a field rotates around a point. Another word for that is the rotational of a vector. Line integral, which measures the amount of work done by a field around or over a path, over a trajectory. And flux, which measures the density of a field passing through a surface, like heat, like electromagnetic flux, etc. And again, the gradient is a vector that designates the highest increase in a function. We get that by deriving the function in respect of x and y. Typical vector fields. Here we are presenting conventional functions of vectors that are often seen in nature. They are more common, so to speak. First, you have the radial field. fxy is equal to xy. The vector points outwardly from the origin. For this vector field, the vector size increases with distance. Second, rotational field, fxy is equal to minus yx. Vectors are tangent to the circle around the origin. And constant field, fxy is equal to 2, 4, for example. The vectors in such case have the same value everywhere, so it is a constant vector. Example, find the divergence of fxy equal x squared plus y squared. Nabla f, this is the divergence, is equal to partial derivative in respect of x, then in respect of y of the function fxy, equal 2x and 2y. So this vector, which is the divergence of the function, points outwardly from the origin, and it increases linearly with distance, because as x and y increase, the vectors move away gradually from the origin. Line integral. A line integral of a vector field along a curve measures the work done by the vector field along that curve. The length of the curve can be computed by integrating the magnitude of the curve's tangent vector, like you see in the below picture. So work done by a vector field over a curve is given by W equal integral over C FDR equal integral from A to B, which are the boundaries of that length, FRT, so f in function of RT, dot R prime T dt, which is the tangent vector. Length of a curve, L is equal integral over C ds is equal to integral from A to B, R prime T in modulo, meaning the size, the length of each tangent vector, dt, okay? We are integrating it throughout the curve. This is how you get the length of the curve. So it is equal to integral from A to B, R prime T in modulo in size dt. Exercise. Compute the line integral where f, the vector field, is equal to yx, and c is the upper half of the unit circle x squared plus y squared equal 1. Traverse clockwise, which means from -1 to 0 or from pi to 0. Okay, at first we need to parametrize the curve and we need to find f in function of the curve itself. So w, the work, is equal to integral over c, the curve, FDR equal integral from A to B, which are the boundaries, FR of t dot R prime of t dt. We will see what we mean by parametrization. Okay, So this is a circular curve. So we need to transfer to polar coordinates. Let's switch to polar. X equal r cosine theta, y equal r sine theta. The radius is constant along the path. What is changing is the angle, so we'll consider theta as t. Radius r is equal to 1. fxy is equal to yx. fr of t is equal to sine t cosine t. So y and x, we find them in respect of rt. Y becomes sine t and x cosine t. R of t is equal to xy. It has two components. What is x? X is equal to cosine t. Y is equal to sine t. R prime of t is the derivative of rt, which means it is the derivative of x and y in respect of t, equal minus sine t cosine t. W equal integral over the curve C f dr equal integral from a to b frt dot r prime of t dt equal integral from pi to 0 sine t cosine t dot minus sine t cosine t dt, which is equal to minus sine square t plus cosine square t equal 1 minus 2 sine square t dt. As a reminder, cosine a plus b equal cosine a cosine b minus sine a sine b, cosine a minus b equal cosine a cosine b, plus sine a sine b. 2 sine a sine b is equal to cosine a minus b minus cosine a plus b. Okay, we've added both of the first and second equation, but we multiplied the equation over the top by minus so that we won't cancel out sine a sine b but cosine a cosine b instead. 2 sine a sine b equal cosine a minus b minus cosine a plus b. So sine a sine b is equal 1/2 cosine a minus b minus cosine a plus b. So sine square theta is equal to 1/2 1 minus cosine to theta. So integral from pi to 0, 1 minus 2 sine square t equal integral of 1 minus 2 divided by 2, 1 minus cosine 2t. We simply replace the value of sine square t in this equation equal integral from pi to 0 cosine 2t dt equal 1/2 sine 2t between pi and 0, which is 0. Compute the line integral where fxy is equal to x squared xy and c is the line segment from point 0, 0 to 1, 2. So let's trace the path. It is from 0, 0 to 1, 2, which is a line. Okay, what is the equation of the line? We have two methods in finding the line equation. The first one, we fill the coordinates of both points in the general line equation, y equal ax plus b. So 0 is equal to 0 plus b. 2, which is the y of the second point, is equal to a times 1 x of the second point plus b. So a equal 2, b equals 0. Another method is a equal rise over tread. Rise, how much the function is rising, over horizontal displacement, which is the x displacement. And b is the elevation from the x-axis. Since this line is not elevated from the x-axis, it intersects with the origin of the axis, so b is equal to 0, and rise over tread is 2 divided by 1. That's why the equation for the function is given by y equal to x, with x given as t. We're going to parameterize x as being t. So the elevation is 0, b equals 0, because the line starts from the origin. The line height from x-axis is 0, and a equal rise over tread, 2 divided by 1, which is 2. Let x equal t, y equal to t. R of t is equal to xy equal to x is t, and y equal to t. This is the vector rt. R of t is equal to t, which are the coordinates or the parameters for x and y. R prime of t, the first derivative, is equal to 1, 2. So in order to find the line integral of the function fxy, we're going to integrate f in respect of rt throughout this line. So fxy is equal to x squared xy, which is t squared 2t squared. That's fr of t. W is equal integral from 0 to 1 fr of t, because the parameter is t, which was x. Okay, it is from 0 to 1 fr of t dot r prime of t dt equal integral from 0 to 1 t squared 2t squared dot 1 2, which is r prime of t dt equal integral from 0 to 1, this is a dot product of t squared plus 4t squared, which is 5t squared. 5 is removed to the outside. Integral from 0 to 1 t squared dt equal 5 times t to the power of 3 divided by 3 between 1 and 0, which is 5 over 3. The work done by fxy over y equal 2t. Another one, compute the line integral where fxy is equal to y squared to xy along see the parabola of equation y equal x squared from 0 0 to 1 1. Of course, you can try to solve it yourself. Now, let x equal t, then y equal t squared along the curve. Then r of t is given by t squared or x, y. Then the derivative along the curve is given by r prime of t is equal to 1 to t. fxy is equal to y squared to xy. Fr of t, or in respect to r of t, is equal to t to the power of 4, because t squared squared, to xy, which is 2 times t squared, or 2t to the power of 3. Then the work done is equal to integral from 0 to 1 fr of t dot r prime of t dt. So w is equal to integral from 0 to 1 dot product between fxy, fr of t right now, t to the power of 4, 2t to the power of 3 dot 1 to t, the derivative of r of t. W is equal to integral from 0 to 1 t4 plus 4t to the power of 4 dt is equal to 5 t5 over 5 equal to 5 over 5 equal 1. The work done by the field vector over this curve is equal to 1. Fundamental theorem of line integrals. If fxy is a gradient of a function f, that fxy is equal to nabla f, in other words, the line integral fxy along a path C between 2 points A and B, which are the boundaries, only depends on these endpoints regardless of the path traveled. The vector field should be conservative for that to work out. We witness this concept in physics as we evaluate the work done by a force F on a solid. For example, the wind over an airfoil. The work value is independent of the path traveled, but rather the start and end points of the stream you're measuring. Okay, so W is equal to integral from B to A, or A to B, FRT dot R prime of T dt is equal to FB minus FA. That's why the line integral of a function around a closed loop is 0, given that the start and end points are the same. So you haven't gone anywhere. Integral over C of f dr would be equal to 0. This theorem is applicable only when f is conservative, f equal nabla f, curl f is equal to 0. There's no rotation in the vector field. C also should be a continuous path with no disconnections or discontinuities. Computing the curl. What is the curl? Another word for that is rotational. Let's say you have a function fxyz is equal to pxyz, the first component in the x direction, times vector I, the unitary vector on x, plus qxyz j, plus rxyz k on the z-axis. Curl f is equal to nabla rotational f. It's equal to, you place I, j, k, the unitary vectors on top, then partial derivative over x, partial derivative over y, partial derivative over z, and pqr, and you multiply them together. So curl f is equal to I times partial over partial y times r minus partial of q, derivative of q over z, minus j, this is where they intersect, and you multiply partial r over partial x, the derivative of r in respect of x, minus the derivative of p in respect of z, plus k times partial q over x minus partial p over y. This should be 0 when the field is conservative because there would be no rotation in this field vector. For a 2D vector, fxy is equal to pxy I plus qxyj. So how do we compute the curl? It is nabla cross f equal partial of q in respect of x minus partial of p in respect of y, where p and q are the first and second component in respect of x and y axis, equal derivative of q in respect of x minus derivative of p in respect of y. Curl f is equal to 0 again when the vector is conservative, which means partial q over partial x minus partial p over partial y is equal to 0, or partial q over x equal partial p over y. Technically, the divergence of a vector field measures how much that field is flowing out when the divergence is positive, or sinking down when the divergence is negative at a specific point. So when its value is 0, then the field is static at that point. It means that the field is parallel to that surface. Example of negative divergence: water flowing into the inlet of a water turbine, as you see in the right figure, where you have a Francis turbine in the picture. So how does the sign plus or minus of the divergence determine the flow direction? Nabla f is equal to partial f over x plus partial f over y plus partial f over z. If the divergence is negative, the flow is inward, otherwise it is outward, and if it's equal to 0, then there's no flow from or to the surface. How does the sign plus or minus of the divergence determine the flow direction? Okay, as a reminder, the derivative of a function in a specific direction, x, y, or z, give us the slope of the tangent in that direction. If it's positive, the slope is going up. If it's negative, the slope is going down. And if the derivative is parallel, 0 rather, then the function, vector field in this case, is parallel to the axis, so neither flowing in nor flowing out. It is the same concept as calculus 1 when you have a calculation of the slope of a function. That slope, if it's positive, it means that the function is going up. If it's negative, it's going down. Otherwise, if it's 0, then the function is parallel to the x-axis. For a vector field f defined by fxyz is equal to pxyz times I plus qxyzj plus rxyzk, divergence is given by nabla.f is equal to derivative of f in respect of x plus derivative in respect of y plus derivative in respect of z. For a volumetric region, n is the normal vector over the surface ds. So f dot n gives us the direction of the magnitude of the vector at that point. The dot product between f and the normal vector gives us the direction of the magnitude of the vector at that point, how it is going. The integration over a region would give us the full flux in that region. So divergence at a given point is nabla f is equal to limit p going to 0, 1 over v. So it is the limit for an infinitesimal point, integral dv fn ds. Okay, so it is the integral of the flux divided by the entire volume, which gives us the flux over one point where v goes to or tends to 0. F dot n ds. N is the normal vector and f is the value of the field at that point. Green's theorem. What is Green's theorem? It converts a line integral around a curve to a double integral of the region area bounded by that curve. C should be simple, continuous, and a closed loop, a closed curve forming a region R on the inner enclosure for that theorem to work out. Fxy, let's say, is the field acting on region R and having continuous partial derivatives. It should have continuous partial derivatives given by fxy equal p xy I plus q xy j. I equal closed integral ftr is equal to double integral over the region R, which is enclosed by the loop, by the path of derivative of q divided by x minus partial p over y dx dy, which is the rotational of this vector. Okay, this is actually the curl or measurement of rotation, circulation of field F around the curve C. Curl F is equal to nabla cross F equal to partial Q over X minus partial P over Y. So we can equate the line integral and convert it into a double integral whenever we have or we are dealing with a closed loop. A path that is closed can be converted from line integral to double integral to evaluate the work over a function. Let's practice. Use Green's theorem to compute the following line integral fxy equal y x squared, where C is the circle, x squared plus y squared equal 1. Remember, we need a closed loop, and here a circle is closed. Oriented counterclockwise, so it is rotating from 0 to 2 pi in this direction. Okay, let's convert it into a double integral. So I equal O integral over the curve C f dr is equal to double integral over the region R, partial Q over partial X minus partial P over partial Y, which is the rotational or the curl of F, dx dy. P is equal to Y and Q is equal to X squared. So I equal integral over R partial Q over X, which is 2x, minus partial P over Y, which is 1. So 2x minus 1 dx dy. Then you need to transfer to polar coordinates. So x equal R cosine theta, y equal R sine theta, R between 0 and 1, theta between 0 and 2 pi, and dx dy is equal to R dr d theta. I equal to integral from 0 to 2 pi, integral from 0 to 1, 2R cosine theta minus 1 R dr d theta. So I is equal integral from 0 to pi. We integrate in respect of R, so you get 2R power 3 divided by 3 cosine theta minus R squared divided by 2, because you have R here on the outside, which is integral from 0 to 2 pi, 2/3 cosine theta minus 1 over 2 d theta equal 2/3 sine theta minus 1/2 theta between 2 pi and 0, which is minus pi. Find the curl or rotational of the following vector and then evaluate its value at point 1, 2, 3. The function is given by fxyz equal yz, xz, xy, pqr respectively. You can try to solve it yourself. Let's move on. Curl f is equal to nabla cross f equal ijk, partial over x, partial over y, partial over z, and pqr, which is equal to I times partial r over y minus partial q over z, which means derivative of r in respect of y minus derivative of q in respect of z, minus j, because it is the middle component, times partial r in respect of x minus partial p in respect of z, plus k times partial q in respect of x minus partial p in respect of y. Nabla f equal I x minus j, y minus y, plus k, z minus z equal 0. So the curl is 0, there is no rotation. At point 1 to 3, the same thing, the curl is still 0, 0, 0, also just like everywhere else. Another one, find the curl or rotational of the following vector and then evaluate its value at point 1, 1, 1. fxyz is given by minus y, x, xyz, which are pqr respectively. Curl f is nabla cross f ijk partial over x over y over z pqr equal I xz minus j yz plus k times 1 minus 1. So curl f is equal to I xz plus j minus yz plus 2k. This is 1 minus 1, which makes 2. Curl or rotation vector at point 1, 1, 1 is, you place 1, 1, 1 in this equation. So x equal 1, y equal 1, and z equal 1. It gives you 1 minus 1, 2. Compute the divergence of the following vector field and then evaluate it at 1, 1, 1. fxyz is equal to x squared y y square z, z square x, which are PQR. The divergence, remember, it's different than the rotational. So nabla f is given by derivative of p in respect of x plus derivative of q in respect of y plus partial r over partial z, or derivative of r in respect of z, equal to xy plus 2yz plus 2zx. At point 1, 1, 1, the divergence is, you place 1, 1, 1 in x, y, z respectively, equal 2 plus 2 plus 2 equals 6, which is positive, so it is an outflow. So divergence of f at 1, 1, 1 is equal to plus 6. Another one on divergence: compute the divergence of the following vector field and then evaluate it at 1, 2, 3. Fx, y, z is equal to minus x minus y minus z. So nabla f is equal to partial p over x, derivative of p in respect of x, then q in respect of y, then r in respect of z, which is equal to minus 1, minus 1, minus 1, or minus 3. It's a constant inbound flow. Why? Because it is negative. So on all points, it is an incoming flow traversing the surface inwardly. This includes also the point 1, 2, 3. Parametric surface. Definition: surface parametrization is a way to describe a surface using two components, u and v. Just as we use t as a curve parameter for line integrals, for a 2D surface we need two parameters instead of one. So a surface S can be described by a vector function RUV, where at each point on the surface a positional vector is protruding or slanting from the origin to localize each point on the surface S in respect of two parameters u and v. So RUV is equal to XUV, YUV, and ZUV. X, Y, and Z need to be translated to u and v components. UV belongs to D, which is the domain or region where the surface exists. This is what the domain would look like. You have a curve over a 2D space. U and V are the components of a vector which is a rotational, or a curve over the surface equal to U cross V. So U cross V gives us the surface element, which is a normal vector to the surface. Remember, the cross product is a normal vector over these two vectors, and its length defines the area or the surface between U and V, which is the surface of that small patch. So the magnitude of this vector is the surface du dv. ds is the surface component equal to Ru cross Rv du dv. ds in magnitude is equal to the modulo or the size of Ru cross Rv. It gives us the surface of that small differential area through the magnitude of the curl Ru cross Rv. When we integrate it over the region, you get the surface of the entire area. So for a scalar function, if fxyz is equal to 1, then fxyz ds is equal to integral over d fruv times Ru cross Rv du dv. It gives us the surface area by adding up the magnitude of all tiny differential surface elements throughout the curve. If xyz is different than 1, suppose f is a density function, the integral gives us the overall density on that surface, or technically the mass of that surface. F can be any type of quantitative parameter such as density, flux, heat, or electromagnetic charge. Let's talk about Stokes theorem, which is the upgrade of Green's theorem for 2D space, taken from the curve to the space calculation level. Just like the curl in Green's theorem computes the flux around a closed loop path, Stokes' theorem uses the curl to compute the flux piercing a surface. S is the closed surface with a boundary C. F is the field vector where S is plunged, is immersed within a field vector. Double integral over D region of nabla cross F dot ds is equal to integral over a curve FDR. Then another translation for that is equal to double integral of n dot ds. N is the normal vector and ds is the superficial element, also equal to fdr. Okay, that's another translation for that. Nabla cross f dot ds is equal to n ds. This is what we're talking about, because the cross product again is actually the normal vector to the surface multiplied by ds, the surface element, so it gives you n ds. Example, evaluating the surface of a sphere with radius r equal to using uv vector parameters. The equation of the sphere is x squared plus y squared plus z squared equal to 4. Now, what we're talking about is the surface layer of the sphere. That's the surface not of a sectional disk of the sphere, but rather it is the sphere itself from the outside. We are evaluating its surface. The formula for that, by the way, is 4 pi r squared. So let's evaluate it using a surface integral. It's given by double integral over d, which is the region, ru cross rv du dv. Moving to spherical coordinates. So what are x, y, z in respect of u and v? X equal to sine phi cosine theta, y equal to sine phi sine theta, these are the spherical coordinates, and z equal to cosine phi. We need to designate phi as u and theta as v to move on. So u equal phi, v equal theta, u is between 0 and pi, and v is between 0 and 2 pi. So r is equal to 2 sine phi cosine theta, which is 2 sine u cosine v, 2 sine u sine v, and 2 cosine u. These are the parameters of r. Remember, r has x, y, z. So what are these three components? X is equal to 2 sine u cosine v, y equal to sine u sine v, and z equal to cosine u, with u being phi and theta being v. We are following this equation. Okay, so at first we need to derive in respect of u. What is ru? Ru here is the derivative of r in respect of u, which is 2 cosine u cosine v, 2 cosine u sine v, and then minus 2 sine u. We are deriving in respect of u to get the ru component. Then we need to get the rv, which is the derivative of r in respect of v. So rv equal partial r over v, which is, okay, deriving in respect of v, minus 2 sine u sine v, 2 sine u cosine v. Then in respect of v, the third element is 0. We've gotten ru and rv. Now we need to cross them to get the cross product of these two vectors. Okay, so ru cross rv is equal to ijk. First, place the components of ru, which are 2 cosine u cosine v, 2 cosine u sine v, and minus 2 sine u. Then rv, which are minus 2 sine u sine v, 2 sine u cosine v, and 0. We multiply, so you get ru cross rv is equal to I 0 plus 4 sine square u cosine v minus j times 0 minus 4 sine square u sine v plus k, which is 4 sine u cosine square v minus, and you multiply the minus here by the minus of 2 sine u sine v, so you get 4 cosine u sine u and sine square v. By the way, we can get these as the same factor and get rid of cosine square v plus sine square v. So 4 sine u cosine u times cosine square v plus sine square v, which is 1. Now after that, ru cross rv as a modulo, as a size, is equal to square root of x squared, which is 4 sine square u cosine v, plus y squared, which is 4 sine square u sine v, plus 16, which is, the last component, 16 sine square u cosine square u, equal to 16 sine square u times cosine square v plus sine square v, which is also 1, plus 16 sine square u cosine square u. We get rid of that, it gives us 1. So it is equal to 16 sine square u times sine square u plus cosine square u, also 1, equal 4 sine u. Then you integrate it. U is between 0 and pi. V is between 0 and 2 pi. So I equal integral from 0 to 2 pi, 0 to pi, 4 sine u du dv. I equal 4 integral from 0 to 2 pi of minus cosine u, the integral of sine u. 4 is on the outside between pi and 0, which is 4 integral from 0 to 2 pi, 1 plus 1, which is equal to 16 pi. Okay? 8 integral from 0 to 2 pi dv is equal to 8 times 2 pi minus 0, 16 pi. Let's check it. The surface of a sphere is given by 4 pi r square, with r is equal to, so 4 pi r square is equal to 4 pi times r square or 2 square, which is 4, equals 16 pi. Evaluate the surface integral of the following vector field over surface S. fxyz is given by xyz. S is a plane pointing up with equation z equal 1 minus x minus y, and z is greater than or equal to 0. That's the surface here, or the region rather. Drawing the surface. For x equals 0, y equals 0, z equals 1. For x equals 0, y equals 1, z equals 0. And for x equals 0, y equals 1, z is equal to 0. Okay, so for x0, z0, y is equal to 1. These are the 3 points that are bounding the region where we are calculating the flux over that surface. So x varies from 0 to 1. This is y. It varies from 0 to y equal x, okay, to x. This is how it changes. I equal integral, double integral over s f ds is equal to integral over s fxy dot n dx dy. N is rx cross ry. So we need to find n. And again, these are the 3 points. X is changing between 0 and 1. Y is changing between 0 and y equal x. Okay, that's the equation. So it's changing between a point and a function, which is y equal x. R is given by x, y, z. Let's find x, y, and z. Rx is equal to the derivative of r over x, derivation of x over x, equal 1. Then derivation of y over x is 0. The derivation of z is z prime x, because z is complex. Z is equal to 1 minus x minus y. It's not a simple function. Then ry is equal to derivative of r over y. So it gives us, for x, derivation of x over y is 0. For y, 1. For z, it is z prime y. It is to be evaluated next, okay? Because z is expressed in function of x and y. Rx is equal to 1, 0, and the derivation of z in respect of x is minus 1. Could have replaced z by 1 minus x minus y over here. For simplicity, I've left it as z. As for y, z prime of y is also minus 1. These are the 2 parametric vectors. Rx cross ry equal ijk, then the components of x, 1, 0, minus 1, then the components of ry, 0, 1, minus 1. You multiply them together and you get I plus j plus k. That's the n vector, by the way, which is rx cross ry. A short-handed solution, by the way, that you can use is, instead of making this entire calculation, you derive z according to x, multiply minus sign behind it, so minus f prime x, then minus f prime y, then 1. Integral f ds equal integral fxy dot n dx dy over the s region, n equal 1, 1, 1, which is rx cross ry. We just evaluated it. I equal integral x is from 0 to 1, y from 0 to x. If you notice, we have fixed one variable. So we fixed z. That's why the variables for the double integral are x and y. We are deriving in respect of y and x. Okay? So z needs to be expressed in function of y and x. It's not a triple integral, it's a double integral. So integral from 0 to 1, from 0 to x, x, y, z, dot 1, 1, 1, dy, dx. That's x, y, z of f. 1, 1, 1 is the n vector we just evaluated, equal x plus y plus z, which is 1 minus x minus y, which is 1 dy dx, between 0 and x for dy and 0 and 1 for dx, equal integral from 0 to 1 y from x to 0 dx, equal integral from 0 to 1 x dx, x2 divided by 2 between 1 and 0, equal 1 over 2. Evaluate the surface integral of the following vector field over surface S. fxyz, the vector field, is equal to 0, 0, z, and S is the paraboloid of equation z equal 4 minus x square minus y square above the xy plane. Now, if you notice something, when z is equal to 0, the projection of this paraboloid over the xy plane is a circle of equation x square plus y square equal 4, having the radius r equal 2. At z equals 0, the projection again of this surface over the xy plane is the circle x square plus y square equal 4 with radius 2. We need to transition to polar coordinates and expressing z in terms of x and y. So x equal 2 cosine theta, y equal 2 sine theta, and the normal vector is equal to rx cross ry equal, we will use the short-handed method, minus f prime x minus f prime y and 1. So derivative of z in respect of x is minus 2x, and minus here you get plus 2x. For y, it is minus 2y times minus 1 plus 2y and 1. So n is equal to 2x, 2y, and 1. N is expressed in terms of r and theta as 4 cosine theta, 4 sine theta, and 1. F is equal to 0, 0, z, or 0, 0, 4 minus x square minus y square, which is equal to 4 minus r square times cosine square theta plus sine square theta, or 4 minus r square. Because remember that x is equal to 2 cosine theta and y equal 2 sine theta. So I equal integral f ds equal double integral over s fxy and dx dy. So we have all the components needed. Let's integrate. I equal double integral over s f dot n dx dy is equal to integral from 0 to 2 pi, 0, 2 for the radius, 0, 0, 4 minus r square dot n, which is 4 cosine theta, 4 sine theta, and 1. Okay, this is n, and this is the vector field, times r d theta, equal integral from 0 to 2 pi, integral from 0 to 2, 4 minus r square, times 1, r d theta, equal integral from 0 to 2 pi, 4 r squared divided by 2, r to the power of 4 divided by 4, between 2 and 0, is equal to 8 pi. Divergence or Gauss's theorem. The divergence theorem is a concept that relates a surface integral over a closed surface S to a volume integral of the region inside that surface. The mathematical interpretation is double integral over a region D, Fn ds, is equal to the triple integral over a volumetric region E, nabla dot f dv. S is the closed surface, n is the outward normal vector on the surface, v is the volume of S, f is the vector field on that surface in both cases, f dot n is the dot product between the vector field and the surface normal vector. A simpler analogy of this theorem, imagine a flux traversing a surface S, like the right picture here. Picture the flux as the airflow going through an opening. So the flux of water or air, whatever, traversing the surface is equal to the amount of water within the volume itself, since the same water on the inside has to flow to the outside of that box. This is the concept here. So the flow of a fluid, let's say, going through a surface is equal to the actual flow that is trapped within the volume, dripping that flow outside through that surface opening. This is the concept of the divergence theorem. Exercise: let fxyz be equal to x squared I plus y squared j plus z squared k. S is the surface bounded as follows: x is between 0 and a, y between 0 and a, and z between 0 and a. Double integral over d f and ds is equal to triple integral over the region E nabla.f dv equal integral from 0 to a on the three directions, the derivative or the gradient of the vector f. Remember, nabla f is the gradient, which is 2x plus 2y plus 2z. The derivative of f in respect of x plus in respect of y plus in respect of z, which is equal to 2x plus 2y plus 2z dz dy dx equal to integral from 0 to a xz plus yz plus z squared over 2. We see 2 is a common factor. We pushed it to the outside of the integral, and the integral in respect of z gives us xz plus yz plus z squared over 2. The 2 has been moved to the outside, which was multiplied by all of them. Between a and 0 equal to double integral 0 to a, ax, it is between a and 0, so ax plus ay plus a squared over 2 dy dx equal integral from 0 to a. Here we have integrated in respect of y, so axy plus ay squared over 2 plus a squared over 2y dx equal to a squared x, because it's between a and 0, so you replace y by a squared x plus a3 over 2 plus a3 over 2 equal to integral from 0 to a, it becomes a squared x2 over 2 plus a3 x between a and 0 equal to times a4 over 2 plus a4 equal 3a to the power of 4. Another exercise, you can try of course to solve it yourself before we get into the solution. fxyz is given by yzi plus xzj plus xyk. S is the surface of a cube bounded by 0, 1, 0, 1, and 0, 1 for the three of the coordinates for x, y, and z respectively. Okay. Double integral over d f and ds is equal to triple integral over the region E nabla f dv, which is the gradient. Nabla f is equal to partial of yz in respect of x plus partial of xz in respect of y plus partial of xy in respect of z. It is all 0. Okay, so there's no flux. It is equal to 0. And thank you for watching. That's all.